expanding the Ocean World Club. It's a bit long-winded, so we'll just call it Weird Ocean Worlds, if that's okay by everyone. Welcome. We have a pretty packed agenda, so we're going to have to keep people very, very much on time today. I have been asked to remind people that many people in the room hopefully are Dwarnic judges, and if you're not, it's not too late to volunteer, so please do so, and remember to actually take notes if you're one of the judges. Bill, did you want to add?
Well, let me say, introduce yourself.
Oh, yes, of course. So I'm Carl Mitchell, JPL, and I am a planetary scientist.
I'm Bill McKinnon, a co-chair, and
Mariana Blanco Rojas. I am the moderator, and I am at Purdue University.
well, that's all wonderful. I'll also just remind everybody there's a countdown clock in front of the podium that you'll see your time ticking down, and it will go yellow at 2 minutes before the time ends. And for those who are speaking, please go see the technicians at the side of the room 5 minutes before you're talking to get your lavalier mic installed.
Oh, and if you're aware that anyone can't make it at the last minute, please do come up or at least tell the technicians, because occasionally we have had people that are no-shows. Thank you.
We're done early. We're going to wait, though, till the official time to start at 2:20. Well, again, welcome everybody to this wonderful session on Mimas, Enceladus, and the Uranian moons, expanding the Ocean World Club. And we're about to start as soon as the magic moment occurs. But I will take the prerogative of introducing the first speaker now. So we're going to hear from Roberts, Walker, and Rodin on melty shells, the formation of new habitable environments, and James Roberts will give the talk.
All right, thank you, everyone. Can everyone hear me? Do I need to take this off? We're good? Okay. So ocean worlds are becoming very common in the solar system. There's this nice graphic illustrating some of the known or potential habitable or ocean worlds. in the solar system, some of which may be habitable. Because I prepared this on a Mac and did not test it, this animation is not playing, but this is illustrating that tidal heating is the primary source of heat inside icy worlds. And particularly when you have a liquid ocean separating the ice shell from the refractory material underneath, which is inconsistently referred to as a mantle or a core or a silicate core, even if it may be carbonaceous. We're just going to call it the interior. If you have that mechanical decoupling, it makes it much easier to flex the ice shell and you can get enhanced tidal dissipation. And in fact, that can be quite self-sustaining. Oh, there it is. I just had to hit the button. Long day. However, if the tidally dissipated heat is not sufficient to maintain that situation, you might get freezing of the ocean and thickening of the ice shell. And that will continue to happen until it finds an equilibrium where the heat produced in the interior is equal to the heat flux being lost from the surface. However, once you get to a relatively thin shell, especially, you can enter these resonant peaks of tidal heating in the ocean. And these are most prominent when you get to turning off the screen instead of hitting the laser pointer, which is this button. And, at about 1 kilometer or less, you can get a whole lot of these peaks, but sometimes you can get it even in thicker oceans where you have a sharp increase in the amount of heat dissipated. And so it's very difficult to freeze an ocean entirely. But what if you did? Or what if it started frozen? It was accreted slowly or something, a very low eccentricity, and there was never an ocean for whatever reason. Could you make one? Because in this situation, you have the ice shell coupled to the rocky interior. The rocky interior is much less deformable, and so it holds on to it. And the deformation is highly restricted. Can you ever get out of that state such that you are on the left side of this graphic and then producing an ocean that you would see on the right side after some melting? So we decided to look at this. We have chosen at random, very carefully, 4 moons that we think span the diversity, if I'm allowed to use that word, of icy bodies in the solar system. So we have Europa, Callisto, Enceladus, and Mimas, all shown here to scale, except that Enceladus and Mimas have been inflated by a factor of 3 so that you can actually see them. We've assumed that we have initially frozen interiors, and we model the coupled tidal heating and thermal evolution of these bodies. So our primary free parameters in this situation are the orbital eccentricity and the basal temperature. We're used to holding the bottom temperature at the melting point of water, but if you're entirely frozen, there's no need for that to be the case. So the main question we're trying to answer, is it possible to initiate melting? And I'm going to tell you right now, we haven't got to Callisto yet, even though it's arguably the most interesting of all these. So there are 3 methods that we've considered for how to possibly do this. One is that you have a fluffy core. And that is on the smaller moons, the central pressure is simply not high enough to compress all of the refractory material into a single chunk. So you've got ice filling these interstitial pore spaces, and that can control the deformation. And this example we're showing here for Enceladus, you can see that once you get to about 20% of ice-filled porosity, you're actually dissipating substantial heat in the rocky portion. And at 30% ice-filled porosity, that's where most of it is. So this could work on the smaller bodies, but not larger ones like Europa. The second one, which I've talked about, at length before, is that you could have a giant impact, which is a very convenient solution because it just rains out of the sky and there's nothing you can do about it. We don't see any obvious evidence of giant impacts on Europa and Enceladus, but those surfaces are so young that you wouldn't necessarily expect to preserve it. The older and colder moons, Mimas and Callisto, each show a giant basin. And if you look across the solar system, you do tend to find these almost always. So a question is, could an impact heating produce a thin temporary ocean, even if it will dissipate later? Because the impact heating can warm the ice underneath, and that can jumpstart tidal heating. But the one I want to spend the rest of the time talking about is evolution of the eccentricity. Because orbital eccentricity is a primary factor controlling the level of tidal heating. And if you have a completely frozen interior, that will not be very dissipative, which allows you to pump up the orbital eccentricity and sustain it over much longer timescales. So we're going to invert the question and ask, what are the conditions for a moon to remain frozen? So my colleague, Matt Walker, has done a bunch of these stability envelopes where you plot out where are you in equilibrium for a given basal temperature and heat flux. So to take this example, we've got a basal temperature of 150 Kelvin at the ice-rock interface, and some amount of heat flux. And then we're imagining that the eccentricity increases. The heat flux scales as the square of the eccentricity, so you're at a much higher heat flux. And now the situation will evolve to the right so that the basal temperature heats up until you hit the curve again. So the ice can still be stable and grounded, but at a much warmer basal temperature. And then just for fun, let's assume you heat it up even higher. Now you can see that there is no scenario where Europa's ice can have this basal heat flux and still remain grounded. So the ice shell starts to melt, and we transition from a stability envelope to a zipper plot, where now the free parameter is no longer the basal temperature. You've started to melt, so you're holding that at the melting temperature, whatever that happens to be for the composition. Here we're assuming pure water. That's almost certainly wrong. Now, instead, you've started melting, so the variable parameter is the shell thickness. So to take our example from before, you can find the thickness of the ice shell that's stable under that scenario, and here we have about 57 kilometers. All right, so we seem to be in equilibrium here. And let's imagine that for whatever reason, the eccentricity drops back down, the basal heat flux drops, and you evolve again to the right for a thickening ice shell back to this. So now we have an ocean. The shell configuration accommodates lower basal heat flux without grounding. So getting back to this point, we now have a 1 kilometer thick ocean at the melting point, compared to the initial condition where you had a much colder shell. We've tried running this for the smaller moons, Mimas and Enceladus, and you can see here that the eccentricity values we're having to work with are much higher. So in order to get any significant melting, you need to really crank up the eccentricity. But if you can manage to do that at a sustained orbital eccentricity of, say, 0.03 for Mimas, it melts completely. Even a 1 kilometer ice shell, you can't sustain here. So the present day eccentricity of Mimas is about as high as you can get without melting it. So the takeaway here is that the smaller moons are hard to start melting, but once you do, it's kind of a runaway effect. And then if this was ever higher, you would need to dissipate that heat quickly to circularize the orbit before it has a chance to melt. So here's an example of the stability envelope for Enceladus. We looked at Mimas already. Enceladus is similar to Mimas, but you can get an ice shell to stick around, a thin one. And the present day orbital eccentricity that we have is actually consistent with no melting, but we're pretty sure there's an ocean there. We've got some, very convincing observational evidence, which suggests that Enceladus must have had a very high basal heat flux to begin to melt at some point, and today would require a basal heat source in order to keep from refreezing, which implies that we're in a freezing situation today, even though the ocean is still present.
James, we're out of time.
We're out of time? All right, then I will say that the convection didn't happen. At least nothing interesting happens. And here is a chart summarizing where we are.
Thank you.
Thank you.
We are correct at the time. Right? Yeah. Okay, our next talk be by Rudolph, Roden, Manga, and Walker, Ocean Under Pressure and Eruptions of Liquid Water on Icy Ocean Worlds, and Max Rudolph will give the talk. Take it away, Max.
All right, thanks for the chance to tell you about our ongoing work. What do I need to do to get this?
There it goes.
Oh, okay. That's too much. Okay. No, oh, what's going on?
There's a backwards button.
Okay, I think we're good. Okay, so thanks for the opportunity to tell you about this ongoing work related to the dynamics of thinning ice shells and the generation of vapor and upward transport of vapor and water on icy ocean worlds. So to motivate this, we'll try to address a few global scale geological and geophysical observations related to the icy moons of the outer solar system. Mimas, despite its heavily cratered and geologically dead surface, has orbit and rotation properties that require a decoupled interior. So is an ocean present? And if so, when did it form? And is there perhaps a gap layer, as McKinnon and Schenck have suggested? We'll learn more about that later today. On Miranda, there are unique corona features that have been attributed to convection, and we'll present a possible explanation for that. On Enceladus, there's an ongoing eruption from the tiger stripe fissures at the South Pole. We don't know how that eruption began, but we'll present some ideas related to that. And on Titania, there's a complex geologic history with both compressional and extensional features preserved on the surface. So we'll consider each of these observations or questions in the context of secular changes in ice shell thickness. As a bit of a background, as a planetary ice shell changes in thickness, the volumetric change from water to ice during the thickening phase of ice shell evolution pushes the ice shell outward, and it generates overpressure within the subsurface ocean. Overpressure means pressure larger than the hydrostatic pressure. And it also creates tensile stresses within the ice shell. When an ice shell thins, the opposite occurs. So the volumetric shrinkage from ice to water pulls the ice shell inward. It generates an underpressure within the subsurface ocean, and it generates global compressive stresses within the ice shell. Under extreme scenarios, it's actually possible for the ocean pressure to fall all the way to the triple point of water, which is 612 Pascal, 273.16 Kelvin. And at this point, the surface of the ocean and the base of the ice shell are in equilibrium with vapor. So you can actually start to generate water vapor in a radical scenario deep within a planetary interior. So to explore these processes, we consider geodynamic models. We assume spherical symmetry, so we consider only radial variations, and we solve the equations that describe viscous flow and elasticity coupled with the evolving ocean pressure. We include the effects of thermal expansion and contraction through thermoelasticity, and we include the strongly temperature-dependent viscosity of ice. To show you an example of what the dynamics in a thinning and thickening ice shell can look like, these are previous work. This is previous work examining the response of Enceladus ice shell to long-term variations in tidal dissipation on a 100 million year time scale, which drives ice shell thickening and thinning. And the top panel shows stresses as a function of depth. Blue indicates compression, red indicates tension. And you can see that as the ice shell gets thicker, there are tensile stresses generated. As the ice shell gets thinner, compressive stresses are generated. We also include a model for tensile failure here, and under some circumstances, during the thickening phase of ice shell evolution, we find that it was possible for tensile cracks to connect the surface all the way to the subsurface ocean, perhaps facilitating eruptions. We argued that this was a feasible mechanism for the initiation of activity at Enceladus South Pole. Here we consider the thinning phase of ice shell evolution. So these are similar models, but now we're supplying an excess tidal heating that drives ice shell thinning. The top panel shows temperature and the evolving ice shell thickness. The middle panel shows the deviatoric tensile stresses. You can see that near the surface, there are increasingly compressive stresses, and the basal part of the ice shell is in a state of tension. The bottom panel shows the evolving ocean pressure. So the total pressure at the ocean surface, it decreases from a value of around 4 megapascal all the way to the triple point at the end of this calculation. So at this point, vapor is generated and we terminate the calculation. Once vapor is generated, we can think a little bit about the consequences for planetary evolution and potential implications. So here we illustrate the processes that are occurring at the surface of the ocean. The generation of vapor will also drive any dissolved gases, volatiles, out of solution, while simultaneously rejecting solutes back into the ocean, driving overturning within the subsurface ocean. The accumulation of a layer of water vapor and gases is highly unstable. So there's a large buoyancy associated with the water vapor and exhaled gases. The presence of exhaled gases is very important because we think that as vapor starts to ascend through the ice shell, it will immediately condense to ice. But non-condensable gases, things like carbon dioxide, can migrate upward either through hydrofracture or gas diaparism, or potentially enter the ice shell and form either clathrates or porous ice, both of which are buoyant, and that would drive convective diaparism. Where else can this happen in the solar system? In order to map out parameter space and determine the conditions under which these kinds of things can happen, we use simplified analytic solutions for the ocean overpressure and the elastic response of the ice shell. Here we ignore the thermal contraction of ice, and we assume just a purely elastic layer near the surface overlying a viscous sublayer. These models are developed in a series of papers by Francis Nimmo, by Manga and Wang, and also by Hemingway in 2020. This figure is kind of complicated, so I'll take just a minute to explain. But the horizontal axis shows planetary body radius. The vertical axis shows the mass fraction of water plus ice in the planetary body. And we've mapped out the conditions under which 3 different things happen. First, for small bodies that plot over on the left side of this diagram, it's possible to achieve boiling conditions within the subsurface. It actually turns out to occur for relatively modest amounts of ice shell thinning. This is possible on Enceladus, Mimas, and Miranda. On larger icy bodies, before ocean underpressures low enough to initiate boiling can be achieved, compressive failure occurs within the ice shell, and this limits further decreases in the ocean pressure. You can see that there's a kink in the bottom part of this chart around 900 kilometers radius. This actually reflects a transition from compressive failure in the subsurface to compressive failure at the surface of the planetary body. The third possibility is that neither boiling nor compressive failure of the ice shell is possible. And Europa stands alone among all of the icy bodies in that this process cannot drive either compressive failure or subsurface boiling. So returning to the large-scale observations, we can think a little bit about the implications of ice shell thinning for the formation or lack thereof of geologic features. So looking at Mimas, there's a geologically inactive surface, yet the presence of some kind of decoupling layer between the rocky interior and the icy exterior. And we suggest that there could be a recently formed ocean, and it's plausible that there's a vapor or exhaled gas layer at present, or that one could form. On Miranda, there are these remarkable corona features. They've been attributed to convective diaparism, and this is a body where subsurface boiling is conceivable. And so the exsolution of volatiles from the ocean is a potential mechanism to drive this convective diaparism. On Enceladus, we previously suggested in Hemingway et al. 2020 that downward crack propagation during the thickening phase of ice shell evolution could initiate the geologic activity at the South Pole. The work here presents an intriguing possibility, which is that the boiling induced by ice shell thinning could actually drive upward hydrofracture from the ocean, initiating activity at the South Pole. Finally, on Titania, there's evidence of early tectonic compression followed by extension. And this could be reconciled with a scenario where a passage through an orbital resonance drives ice shell thinning and tectonic compression, followed by thickening and tectonic extension. Finally, the equatorial ridge on Iapetus is one of the most remarkable features in the solar system, and both endogenic and exogenic formation mechanisms have been proposed. It's conceivable that tectonic compression associated with ice shelf thinning during the passage through orbital resonance could explain the formation of a tectonic feature like this. So with that, I'll leave my conclusions. Thank you.
Okay, and so our next speaker will be, in fact, my co-chair, Carl Mitchell, and he'll be speaking on the role of volatiles in driving cryovolcanic ascent and eruption from Enceladus's ocean, feeding its jets. And the co-authors are Rabinovich and Cable.
Okay, thank you. I'm going to take a different position from the last talk because I'm thinking about a model that's more about a thickening ice shelf and pressurizing ocean, analogous in some ways to a magma chamber in terrestrial volcanism. Because on Enceladus, I see plenty of evidence for extension, and to my mind, that is a compelling scenario, one that can't at least be eliminated. So this is a basaltic fissure eruption on Earth, and you can probably see by looking above why I see some appeal to this sort of model, and I will discuss that in more detail as I go through. So why are we interested? We all know about Enceladus. We all want to know how that plume works. It's fantastic. It's fascinating. And frankly, we all love a good mystery. But a big reason why we're very interested in Enceladus's ocean is because Enceladus's plume is because it's likely sampling its ocean. And in order for us to stand chemistry of the ocean, habitability, etc., we need to know how to invert the data that is sampled in the plume in order to infer something about the ocean. And Lucas Pfeiffer did a very nice paper on this a while ago based on an eruption model by Nakajima and Ingersoll. Also, the ability to loft cells up into space is also a function of the eruption model. You can have fractionation that could affect the ability to transfer cells from the ocean into space. So it's key to multiple decadal survey themes. Now, we have a diversity of different models in the community, if you'll excuse the expression, that represent different underlying assumptions and boundary conditions, mechanistic ideas of how the plume works. And on the left, there are two different models, our representation of them. Sorry if there's anything that's not quite exactly as people would communicate from their own model, that both rely on the principle of boiling in order to drive ascent and eruption. The center one is based loosely on the Ingersoll and Nakajima and Ingersoll model from 2016. And in this one, you've got boiling at some depth. It might not be quite as deep as this, but this is just representative. You get fractionation, you get freezing out on the walls, and it's the loss of latent heat through the walls that drives the thermal anomaly that we've all seen. This should be short-lived. They predict a few months, and it should result in highly fractionated products where the concentrations of volatiles in particular are massively increased by the time you get to INMS measurements, for instance. So the ocean would be far more depleted in volatiles than anything else. On the left is an alternative way of looking at it that is very elegant. It acknowledges there were some challenges in some of these boiling models before. It generates the heat from tidal pumping, normal flexing, viscous dissipation. They rely, like the first one, on the idea of a fissure in terms of the geometry, and so you would expect curtain eruptions to come from that. It should be long-lived, though, because the pumping process is sustaining for heat. One of the challenges of this model is it doesn't produce very high velocities. It doesn't produce collimated jets, which we do see, but it is a very nice counterpoint. Most of what I'm going to be talking on today is a different end of the spectrum, which is liquid fueled ascent driven by gas bubble X solution, again, like we see in basaltic volcanism on Earth. There are some extra assumptions we have to make, and there's some that we don't make that contrast with the others. First of all, the thermal anomaly is not the result of conduction of heat from out of the conduit. Second of all, this predicts a very high ice to vapor ratio, and so we need another source of vapor, which is somewhat conveniently predicted by Jay Gogan's paper from 2013 that talked about sublimation ongoing as a result of high temperatures right up to the edge of the vent. And so we kind of accept that that is a free parameter, the sublimation. Let's just go through. Oh, and I should remind you, Dennis Matson talked about this class of model before many years ago. It's rather been neglected as a model, largely because he relied on CO2, which isn't actually the most likely driving volatile in this environment. But it should be said that people have looked at this part of the spectrum before. So there are some challenges with those models that have motivated us. In particular, first of all, Anya Porciunkina in 22 summarized a lot of work that's been going on in the UVIS community, and she found very consistently a set of 37 point source jets throughout the entire Cassini mission. And that suggests there's something going on that's sustained over many years, which is largely inconsistent with Nakajima and Ingersoll, and also requires the evolution to point sources. If you accept that interpretation, which is at odds with Kite and Rubin, which requires wide open fractures in order to get their tidal pumping in that way. Also, both of the previous models neglect the role of the volatiles, which are actually there. And so we really do want to visit that assumption in detail. So a little bit about the life cycle of a volcanic eruption from a pressurized ocean as an analog to a magma chamber. So you have a pressurized source, fractures open up, bottom up, and then they reach the surface, the fissure erupts with the surface. You get a very rapid evolution and self-optimization that tends to minimize energy loss. These are self-optimizing systems to some extent due to feedback between the flow and the walls. And ultimately, you cease eruption once the pressure or volatiles at the source diminish sufficiently. Note this fingering circularization thing is representative of that self-optimization, and we see that all over the place in fissure eruptions on Earth. If you scale the Enceladus ocean to a magma system on Earth that can be sustained for, say, weeks, you can, because the ocean is so massive and the eruption rates are so low, so slow, you can sustain these things for potentially millions of years, way longer than anything basaltic on the Earth. And the bubbles play an extremely important role if there's fire fountaining on Earth. The work done by expanding bubbles drives kinetic energy and potential energy. Either high viscosity or turbulent flow prevents bubbles from migrating and eventually coalescing and getting out of the system and not driving the liquid. But once initiated, turbulence tends to be sustained because you tend to go faster because the bubbles are really successfully driving the flow. And you might be thinking, well, something as low viscosity of water on Enceladus, how does that hold on to its bubbles? But there are circumstances on the Earth where bubbles do drive explosive release. This is a representation of Lake Nyos, which was a lake in Africa that exploded as a result of exsolution of an overturn of a CO2 saturated liquid volume. It killed a lot of people, unfortunately, but it shows us that low viscosity water can explode, which is pretty cool, even in the atmospheric pressure of Earth. We see volatiles. INMS has reported them before. There's a fair amount observed. If we take out the water ice part that using our model that was the only thing that was possible for INMS to observe, we end up with lower concentrations, also almost an order of magnitude lower. But in the case of H2, you end up with a supersaturated amount of H2 in the ocean, even at the top of the ocean. And probably a CH4 as well may play a role. CO2, which was discussed by Matson before, probably doesn't really add anything. And I add that we haven't figured in fully the effects of sublimation on how it might seem to INMS here. But Hedman does show there's a lot of variability of the ice-to-vapor ratio across the plume system, which is consistent with high ice jets, low ice interjets. We solve for conservation of momentum, energy, and mass. Here is our energy equation. Basically, again, the work done by the bubbles adds the potential energy and kinetic energy. Once you've hit a speed limit for kinetic energy, which happens if you've got a supersonic nozzle in the system, then all the rest of the work goes into heat, which stops you from freezing because of all the adiabatic expansion of the bubbles. We actually end up with only 0.3% in this case. Oh, and I should also add, that last one showed a situation for a very low sound speed. With a high sound speed, the kinetic energy becomes far more important. So you can see there's a wide range of kinetic energies with the amount of H2 we were talking about, anything from about 5 to about 200 meters a second. Again, the sound speed in multi-phase flow is quite complex. There may be better models than this, but we suspect in reality, with all of the other volatiles in there, that it'll probably come out as more in the tens of meters a second range for the sound speed. And so another thing to point out is that all of the models we had were fully turbulent, which again supports the idea that bubbles will play a role as long as you can evolve to this situation, which is clearly a big assumption. We have lots of self-consistent eruption models here, even down with these very low concentrations. But I think in reality, once you accommodate things other than H2 in the system, it's going to push it up into that main box to the right. We haven't done the full multi-phase exsolution yet. That's a next step. So in summary, We have a model that we've actually managed to find self-consistent that we don't think fundamentally breaks any of the laws of physics or any of the chemistry understandings. It produces a series of predictions that differ from the other models in the community, including that we rely on sublimation. So if we don't see this sublimation, our model really doesn't work unless the ice to vapor ratios are very wrong. Ocean pressure is favored to be comparable to the overburden pressure, maybe even higher. And evolution from a line or Fisher curtain to a point source is absolutely required. And so that's all I have.
Well, that's wonderful. I now invite all four speakers to return to the podium. Oh, there's one. Oh, I'm sorry.
Never mind.
Oh, never mind. Okay. Well, anyway, we were a few seconds early. So then the final talk of this set, and I apologize, Arnaud, by Matthew, Zacharias, Goldstein, Varghese, and Trefton is simulation of underground hydrogen-bearing cryovolcanism at Enceladus. And Arnaud, Matthew will give the talk.
Thank you very much. So my name is Arnaud Meilleux, working at University of Texas at Austin. I'd like to thank my co-authors and NASA for the grant and Texas Advanced Computing Center for the computations. So as we heard in the previous presentation, INMS detected H2 during the E21 flyover. That's been published by Hunter Waite and colleagues in 2017. You have the main figure of the presentation right here. So this constitutes a compelling evidence of extraterrestrial chemical disequilibrium and possible habitability at an icy world. However, the detections by INMS are variable in time. They're not always present, and the plumes are very narrow, which is weird in the sense that H2 is supposed to be much more diffusive than H2O. So this led us to this project in which we will analyze the underground conditions that could lead to such narrow plumes. So on the top right, you have a sketch of the geometry that we are considering. So you have a crack, circular in our case, with an underground cavern in which we have liquid water, and assuming that walls everywhere obviously are made of ice. At the bottom right, you have the sketch that we're considering. So we're scaling the system with the conduit being a few tens of meters deep. We have an underground reservoir that's also circular. So since we have cylindrical symmetry, we are only analyzing a 1-degree wedge, and all of this using direct simulation Monte Carlo. Forgot to mention in the previous slide that the INMS observations are at 1% in mass fraction at the top. So all of the simulations, that is the default case that I'm going to show, are with that value at the exit. We have around here, you see that we have a contraction that allows the flow to accelerate in the conduit. So we're going to study how all these geometrical parameters do affect the flow within the conduit and at the throat of the conduit. So the length of the conduit, the width of the conduit, the temperature of the icy walls, the position of the contraction, and the size of the reservoir. So these are our default computations. You have here at the top the geometrical parameters, so a vent radius of 2 meters, a conduit depth here of 25 meters, a reservoir size of 10 by 10, H2 mass flux of 10 to the minus 8 kilograms per second per square meter, a nozzle depth of 21 at 21 meters below ground, and a wall temperature constant everywhere, in this case of 240 Kelvin. So on the bottom left, you have the x-axis, which is the radial direction. The z-axis is the vertical direction, so the depth. The H2O number density presented here in panel A is the number density of water vapor saturation, the saturation pressure of water vapor at a temperature of 240 Kelvin, which is decreasing as the water enters into the tube as it is expanding here in vacuum at the surface. Panel B shows the H2 number density field with a zoom here on what's happening at the throat, where you see that basically H2 goes towards the center. Panel C and D are the kinetic temperature and the vertical velocity. where you see the appearance of those structures here, which correspond to shock diamonds. So shock diamonds are observed on Earth in high Mach plumes here with the atmospheric back pressure that you can see them over here, there, and there. And then finally, you have in panel E the velocity streamlines. So the first thing we're going to look at is how H2 influences the flow. So here I present 4 computations. So the first one here is for a constant temperature 240 of all the walls, which are made of ice. And water here at the bottom. The last one here is for a temperature of 220, and in cases in cases 4. So for cases 1, there's H2, 2, there's no H2, 3, H2, and 4, no H2. The last 2 ones here presents the ratio of those H2O H2 number density fields. So what we can see is since when we lower the temperature, the vapor pressure lowers. So that explains why we have lower H2O number density here in the cavern and in the tube. And since the H2 mass flux in kilograms per second per square meter is constant, we have basically more H2 in those cases here, in the case 3 compared to case 4, that you can see here when we compute the ratio of those cases. So the first parameter that we're going to vary is the length of the conduit. So we have 3 cases here with a 5-meter conduit, 10-meter, and 30-meter here. This is the H2 number density. The black arrow, I forgot to mention, refer to the position of the contraction. When we look at how it varies here at the surface, we see that, so looking at those structures here at the top, above 0 meters, that the plume is basically narrower when we have a longer conduit. Here on the right, I also presented the vertical velocities. When we vary the width of the conduit, so here we have 3 cases. On the left with a 2.5, sorry, these are inverted compared to what I plotted here at the bottom. This is a 2.5, a 1 meter, and a half a meter. This is the H2 number density field, and on the right you have the pressure. You see that for a narrower conduit, the H2 pressure increases in the reservoir and also in the conduit. Same that you can see here also when you look at the total pressure of the problem. And the conclusion when you analyze what's happening here at the top is that a narrower conduit leads to narrower H2 plumes at the surface. The next parameter that we looked at is the temperature of the wall, considering 4 cases. The first one, back. The first one is for constant temperature 240 everywhere. The last one is for a constant temperature 220 everywhere. And case 2 is for increasing temperature, as going up in the conduit from 220 to 240. Case C, the opposite, the temperature is decreasing. And we look at the H2 number density based on those parameters. So this is probably the most important parameter to look at, since and because it affects the flow. When the temperature increases here in case 2, you have a lot of water that gets that's coming from the sidewall here, evaporating from the sidewalls, which basically compresses the flow and narrows the plume at the surface. The opposite happens here in case C, when water will have tendency to condense on the walls. The next parameter we look at is the position of the contraction. So as you can see, the contraction here is located right above the reservoir and then increasing in the different cases. As long as the contraction is located a few radii below the surface, we see that in this case, the mixture vertical velocity is not affected at the surface. The only cases in which it is affected are cases 5 and 6 here, where you see that basically all parameters that you're going to look at, the H2 density or the H2O or whatever, will be affected. And the last parameter we looked at is the size of the reservoir. So we considered 4 cases. The first one with a very small reservoir of 5 meters high, 5 meter radius, 10 by 10, 12.5 by 10, 12.5, and 15 by 15, with the contraction always located at the same height. The depth is the same in all those computations. When you look at the H2 number density on the left, and also A, C, E, and G, and the velocity streams, we can see that the H2 plume at the surface is not affected by the size of the reservoir as long as its typical length is much bigger than the width of the conduit. Which takes me to the discussion and conclusion. So I presented here a direct simulation Monte Carlo in which of H2 and H2O, H2 being fluxed in the problem from the bottom, H2O being evaporated and sublimated from the walls and also being able to condense on the walls. The DSMC simulations are resolving the mean free path and the mean collision time, have enough numerical particles, and are all presented at steady state. You saw that we have a complex flow physics because of the presence of all the shock diamonds in the conduit. We studied the influence of several parameters listed here. I got to say this is a work in progress, from which we saw that the width of the conduit and the temperature of the wall are probably the most important parameters. A narrower conduit, which will lead to a narrower plume at the surface, same for actually the length of the conduit, and for the temperature of the wall. It's narrower if the temperature is either constant or decreasing while going up. Position of the contraction is inside the reservoir less important parameters. And then the last question that I didn't talk about is to know whether those conduits have the tendency to stay open or close off. And based on our preliminary simulations, that mainly depends on the temperature vertical profile in the icy walls. Thank you very much.
So you might stay.
I just think the
Yeah, you can undo that. So now it is time for the speakers to take the podium. And people should line up at the microphones or prepare, if you're online, prepare your questions in the Q&A or the chat. Okay. Well, I see our first question from the audience is Kevin Trin.
Hello, everyone. Kevin Trin, graduate student at ASU. Great talk, everyone. My question is for Max. I was wondering, do you think it's plausible that you can have like an? Yeah, I guess you can't see from here. Yeah. Stand up. Go ahead. So, do you think it's plausible that you could have an anhydrous rocky interior at Enceladus in the past, and then with water-rock reactions, you synthetinize the rock, that rock becomes less dense, but because you consume fluid, there's a net decrease in volume, which would create some open space. Do you think that can like create enough under pressure to also drive eruptions?
Yeah, that's not something that we've included in our models, but that would be interesting to think more about.
Okay. Thank you.
I'm Yuba Gary Caltech. I have a question for the first speaker. I apologize, I forgot the name. So I know this was not the main point of your talk, but could you elaborate on how you connect the porosity in the core to the amount of the tidal heating?
Right. So if the core is not consolidated into a single chunk, it's got to be, the pore space has to be filled with something. And that's probably going to be water or ice if it's totally frozen. And if you have enough ice in there, the ice is what controls the deformation rather than the rock. It's the weakest component, so that you can actually get significant amounts of tidal deformation even when it's fully frozen. It's kind of not that intuitive, but the pressure at the center of Enceladus is the same order as the pressure on the surface of Venus. There's just the gravity isn't enough to help.
But with the deformation itself, because you need you need low viscosity, right?
Right.
The deformation alone wouldn't generate heat. What you would need is like some sort of viscous.
Right. So it will depend on what is the viscosity of the ice and how cold that ice is to begin with.
Okay, thanks.
Yep.
Yeah, go ahead.
Also, just wanted to give a chance if you could comment on the final part of your talk that kind of.
Yeah. So all the models that I showed at the beginning were assuming thermal conduction is the only heat loss. So I was starting to run some models with convection in there,
Are you talking about convection in the ice shell or?
in the ice shell, which can remove heat more quickly and can also spread out the low viscosity region. And so there's a trade-off, which effect wins. And by the time I had to submit the slides, I hadn't gotten any results that I thought were interesting. So TBD.
That was quite interesting talk anyways. Thanks.
Thank you.
Hello, Morgan Cable, JPL. James, this one's also for you. You had
Sure.
commented that for the Enceladus model, it looked like the ice shell was thickening again. And I was wondering if you could comment on the timescales of that
Right.
process
So
happening.
the models that I showed do not include latent heat in there. So we don't have the rates yet. That's something we're working on. The convective models will actually have that in there. It'll calculate the melt production or freezing. So we were only looking at equilibrium on this. But you know, the takeaway for the smaller moons is that if you jump the eccentricity up, you can't keep it there very long. You have to circularize it on a time scale that's faster than the melt production.
Well, thank
And
you.
I don't have numbers for it right now.
Yet. And thanks to the organizers. This has been a great session. So thank you guys.
Yeah, this podium is at exactly the wrong spot for the panels.
Hi, Noah Hammond, Providence College. Another question for Max. Yeah, I love the idea of thinking about dissolved gases in the ocean, or if there's if bodies can have a subsurface ocean, can they have a subsurface atmosphere? It sounds ridiculous, but I'm wondering if you could clear something up for me with how I understand overpressure and underpressure and its limits. Is the amount of overpressure in the subsurface ocean related to the tensile stress in the ice shell, and then vice versa for the compressive stress and the underpressure?
Yeah, that's exactly right. So during the thickening phase of ice shell evolution, ocean pressure increases, but ultimately the amount of overpressure in the ocean is limited by the strength of the material. Ice is relatively weak under tension, so that limits the amount of overpressure within an ocean. During the thinning phase, again, the underpressure is limited by the compressive strength of ice, but that's at least an order of magnitude higher than the tensile strength. So you can actually generate quite significant ocean underpressures.
Yeah, that's very cool. And if you could just further comment, I know you said in the thinning phase you get, compressive stresses near the surface, but tension deeper in the ice shell, right? So does that make the ascent of any vapor easier?
Yeah, that's a really good point. So in the shallow part of the ice shell, which behaves like an elastic material, there are really strong compressive stresses. So those are actually a barrier to the ascent all the way to the surface. So it's easier to explain the delivery of material from the ocean actually to the brittle ductile transition. And then what happens after that? Well, I guess we need another grant to be funded.
Well, thank you.
Hi, this is Orkan Umarhan, the SETI Institute. Again, also I want to echo that these are fantastic talks. Thank you very much. These compelling ideas. I would like to ask everyone a question, but I'm going to start with I'll do one with the final speaker. And I wanted to know your simulations. The first question is, would you expect your simulations to scale up to represent what's going on in Enceladus? Obviously, it's linking to Carl's talk, and his ideas. But my question is, do you expect your shock diamonds to remain robust? I hate that word, but because when you go into full 3D, I would expect turbulence to kick in, and it's going to be, hell on Enceladus kind of situation in the tube. So I'm curious to know what you prognosticate that might look like looking forward.
So yeah, the shock diamonds here appear mostly because it's a perfectly cylindrical.
Exactly.
There's nothing else happening. And as you could see on the simulations and in the picture I showed, these only happen over, only a few appearing. They're getting weaker as we go up because of dissipation. So yeah, that would only be true for a very cylindrical one and a narrow.
So do you expect your final predictions for the characteristic scales and of like the speeds and so on to be the same when you have full nearly sonic turbulent conditions? And how do you expect that to relate to Carl's picture that he was pushing in his model?
That's a good question. I'm not sure I can answer straight away to this.
I mean, I can speculate a little bit. I will say that shock diamonds only really happen when you've got an ambient pressure. You need something effectively to reflect off of the outside of the jet envelope. And so I wouldn't expect to actually see shock diamonds unless you were looking down the throat, and then you could create a kind of pseudo ambient pressure.
So in our case, because we have water sublimating from the wall, that's what creates the back.
Okay, you have enough there. Okay, so I mean, you expect to see a transition. What we solve is up to the throat, which actually is where DSMC is nearly where DSMC modeling takes over. And so we only really look at the conduit flow process.
Okay, that's fair.
I see the modeling approaches being compatible. I would say that we can probably make less assumptions of the source properties, which prevents us being as over constrained. But ultimately, I'd love to see these sorts of conduit flow models, not just mine, but Nakajima's Ingersoll, Titan Rubin, coupled with the DSMC type approach fully. I think that would be a really positive way of doing ocean to space modeling.
Okay, well, thank you. Thank you very much.
Thank you.
Excellent stuff.
Okay, right now we're not seeing anyone online with a question, so I'll take the chair's prerogative and also ask the last speaker, Arnaud. What drove the choice of the order of magnitude of your reservoir depth? I mean, why not 300 meters or 3 kilometers?
Computationally feasible. Mostly, yeah. I mean, we need to resolve the mean free path. We need to have enough. So in DSMC, you have collision cells that need to resolve the collision, the mean free path of and the mean collision time also for the simulations. And so if we get way bigger, it would take ages to compute. It's already pretty expensive. So we hope that's something we want to look at also, is to try to scale the problem.
Yeah. And I have a second question. You introduced the topic by saying, how did the H2 jets become so collimated? And I didn't see whether they were really collimated in your output.
They didn't get there. It's a work in progress. So for the moment, we are mostly focusing on understanding everything that's happening below ground. Then we want to go to the next step and understand what's happening above ground. And in this project also, we want to look at other aspects. We assume that we have a circle event. We want to see if other kind of shapes, like a star shape or other things, could create effects in the very sharp angles, and see if those ones could create those very narrow beams.
All right, thank you. Oh, we have another question. Excellent.
My Tribos, Arizona State. This is a question for everyone, but I think it was motivated by Carl's presentation, which was you showed these potential models. So, and you talked about fractionation of volatiles, right? So I'm wondering if you have not just methane, but some organic molecules, which of those models would fractionate these molecules or break apart these molecules the most?
The fractionation we're talking about is not really the breaking. So it was fractionation of bulk composition, and so in which you lose certain elements of the system during ascent and eruption. There's also a kind of pseudo fractionation where the instruments don't see certain elements of the materials. I haven't seen anything compelling that really relates high-speed flow dynamics in this sort of system to molecular breakdown. I wouldn't rule it out. I mean, if you have Mach shocks, for instance, I could see some pretty interesting stuff happening in those Mach diamonds if they're actually happening, which seems likely to me, reasonable, assuming you don't have the Kite and Rubin end member model, which has no such dynamics. But we don't predict anything like that yet.
Okay, thank you.
Noah Hammond again. Question for James. Yeah, it's really fascinating, the subject you brought up about, eccentricity dampening once you have an ocean, but you can pump it up if you're not dissipating too much. And then you mentioned something interesting about Enceladus Mimas, where the eccentricity presently is close to where you said the cutoff was for what it could be without an ocean. And
Right. So
is there some like equilibrium that you were implying there?
well, what I was saying is that if you get Mimas's eccentricity much above where it is now, and the thermophysical properties are similar to what we put in there, and of course we can't measure that super well, then you would start to melt pretty quickly. If you pump it up to about 0.03, and then once you start to melt that ice shell, it melts fast if you don't circularize it back down. But as I said earlier, I don't have time scales for any of this yet. So
Right. And yeah, just thinking about, once if you did generate an ocean, right? We know the dampening time scale is like pretty quick. So like once the eccentricity goes down again, does it get pumped up again and it's like stay near
right,
it
there's
where it would
going to be an iteration, and we couldn't even get through one cycle before I had to deliver the slides. So
Yeah. Anyways, very good work. Thanks.
thank you.
If no one else is asking questions, is there anyone online?
Yes, we do
Oh.
have one question online. A question for Max from Kathleen Krast. What happens on Europa when the ice shell thins?
Oh, so unfortunately, it's a little bit boring on Europa. As the ice shell thins, the ocean under pressure can't become large enough to boil, and it also can't be large enough to create compressive stresses that exceed the strength of materials. So nothing happens. Yeah, the gravity's too high.
Do we have any other questions in the room?
I have a question for James. Could you wake Triton from the dead? Because that's a case of pretty extreme change in eccentricity.
This work was funded by a PSIE grant, which is why it's focused on Europa. But if you have some hot, buttery Triton cash money, then yes. It doesn't even have to be hot or buttery. Probably better if it's not.
I think the S-cubed program would be a good target for that.
All right, then.
Hi, Alyssa Roden, Southwest Research Institute. My question is not a question, it's a comment, and it's not for you, it's for Noah. So the work that we did looking at how ice shell thickness, dissipation, and eccentricity evolution occur together showed that you can only sustain an ocean for about 10 million years because of exactly this effect. So as soon as you begin to melt, you dissipate a lot. As you dissipate, you lose eccentricity, which reduces your dissipation. So you thin the ocean and then you thicken. And as long as you're thinning more slowly than your eccentricity is decreasing, you never lose the entire ice shell. If you stayed in that situation through, say, a mean motion resonance like Enceladus, you would eventually lose the entire ocean on Mimas. Thanks.
I see no more questions. Does anyone want to come up to the microphone? We can pause for a bit if you prefer. We have 2 minutes, a whole 2 minutes of pause. You can breathe.
There once was a moon called Europa, where astrobiologists hope a critter or three may swim in the sea beneath the icy dystopia.
Well, I think that seems like the perfect time to wrap up that part of the session. Is the next speaker ready and mic'd up? Oh, yes, you are. Perfect. Okay, we only have a few seconds until the next part of the session is due to start. So I'm sure our speaker, Bill McKinnon, doesn't need any introduction, but Bill is going to be talking about, is Mimas a Dyson satellite? The fate of small melting moons. So this is a pretty extreme end case compared with some of the other models. Thank you very much.
Oh, we'll
Bill.
see. We'll see. Okay. So planetary volume change is an extraordinary, or can be an extraordinary, driver for global tectonics, right? The poster child for this is Mercury, the first and classic example. Mercury, as revealed by Mariner 10 and Messenger, is covered with shortening structures of all sorts, including the famous lobate scarps. When you look at all of the structures together, you estimate a radius change, a shrinkage of Mercury entirely of up to 7 kilometers. And this almost certainly is due to the partial freezing of Mercury's massive iron core. Now, of course, this is going to be a talk about icy satellites, and on icy satellites, it's the change from ice to water or water to ice that drives these strong volume changes. And just like some of the previous talks have mentioned, and I'm particularly interested in smaller icy satellites, in which when the ocean, when the water ice turns into water, you lose a lot of volume. And if for a smaller mid-sized satellite, there's no way actually that if the ice shell is strong enough, it won't be able to match the effective radius change, and you can't really make the water less dense than it is by very much. And so you're going to have basically cavitation, and the water will back away from the shell, and it will be free. Now, this is a more general problem because it's not just melting in small icy satellites. You could have a porous ice rock satellite, and it warms up on the inside, and the internal porosity could collapse. And then if the shell, or a cold icy shell or lithosphere, doesn't move inward, then you're going to have increased porosity at some intermediate level, and you're going to also lose shell support. Now, this is interesting because there is both libration and astrometric evidence that Mimas has an internal ocean. In fact, a substantial internal ocean. And in fact, the more recent paper by Laney et al. Argues that the shell has to be on the order of 20 to 30 kilometers thick, which I'll remind everybody is the same thickness that we now know Enceladus' shell is. But there's no endogenic, activity on Mimas comparable to Enceladus at all. So, and as an example, right, there's no evidence for the viscous relaxation of the big crater Herschel. There's already 10 kilometers deep, a good fraction of that shell thickness that I just quoted. Plus, of course, the formation of Herschel would have blown through that shell. So this clearly didn't happen. So how do you put this all together? How do you reconcile this? Well, Laney et al. Came up with this very clever idea, and that is that the ocean is new. Okay, it only formed 10 to 15 million years ago, just in the way that James Roberts was talking about, that if you start Mimas, just postulate that it has a very high eccentricity, let's say 0.06, then you get a lot of tidal heating, and the shell will start to thin from 100 kilometers, and just in about 10 million years, you'll get down to 25. Okay, so this way, the ocean is young, it post-dates the formation of Herschel. And in fact, it happens so quickly that the thermal wave doesn't have any time to move into the outer part of the shell and affect the surface in any obvious way. But the problem, of course, with this is that, if in fact Mimas, the volume change involved in creating this ocean that Laney et al. Proposed is equivalent to a very large radius change of several kilometers, and a much larger percentage change in the radius of the body compared to Mercury, which would generate enormous compressive stresses in the shell at the kilobar level, and it would certainly fail. So the question I want to address is, well, what if the shell actually is strong enough to support itself and doesn't move inward? Okay, so we go back to this problem, and so you can actually set up the whole thing. You could solve the equation of equilibrium, which is down here for the displacement U. Okay, under the circumstance where there's not only pressure 0 at the surface of the body, but also pressure at the inside of this now free shell. And so this is what that solution looks like. It's completely general for a body of a given density. The displacement is normalized to the radius of the body, and it's in units of rho g r over E, where g is now the surface gravity and E is the elastic Young's modulus. And you can see as the shell is thinner and thinner and thinner, if it's self-supporting by its own gravity and the gravity of the internal body, then you get a certain amount of displacement. And if you want to, this is just, of course, a normalized sense. If you let's use Mimas units to make it sort of realistic, or if you like, real units. So this is what the case for Mimas would be in Mimas units. So for a shell thickness of 25 kilometers, like Laney et al. Proposed, you get 100 meters of internal radial displacement inward, not kilometers worth. So you have the displacement, you've got the strain, then you've got the stresses. So what do the stresses look like? So here's just for that 25 kilometer shell. The radial stress, sigma RR, is close to 0 all the way through, which you expect. But the membrane stress, the in-plane stress in the entire shell is now on the order of 6 to 7 megapascals, which is a large number for icy satellite tectonics as we have studied icy bodies in the solar system. Now, you can compare it to the unconfined compressive strength of solid pure laboratory ice. And if it's cold, if the ice is cold, as the surface of Mimas is, then it will in fact support that kind of stress. But if the ice is cracked, if the ice is fractured, the shell will not be able to support that stress. The unconfined compressive stress of cracked ice is no more than a few megapascals and probably lower. If so, this model then predicts that, in fact, we should see compressive, effects on the surface of Mimas. And everywhere we look on Mimas, we don't see any. Paul Schenk and I, so the next talk is really, we'll go into this. Even the best examples of what were mapped by other workers as ridges look actually extensional to us. And in fact, certainly then none of them are very young features. So, is Mimas a Dyson satellite? So I'm referring to, of course, the fanciful idea of the late physicist Freeman Dyson for a sort of mega technostructure erected by an alien civilization around a star. What are the possibilities? Well, maybe actually Mimas's shell does have compressive features that we just haven't seen because they're all somehow below the resolution of all the Cassini images as good as they are. So this is a bit convenient, but maybe that's a possibility. Or, for some reason, Mimas's icy shell in compression is stronger than all of the other icy satellites that we have studied. It's an interesting thing to think about, this concept of a gap inside of a small body, because in the traditional Dyson sense, the perfectly circular shell will have no gravity on the inside because the potential will be flat. Okay, and so in that way, the ocean and the core of Mimas could bob around. But that's probably unlikely because it's really an ellipsoid, a triaxial ellipsoid, and the interior is the same way. And so they would, in fact, center and, in fact, align. There's also the possibility of gas that was brought up in Max Rudolph's talk. The water ocean on the inside, even with a gap, will give you about 6 millibars of vapor pressure, as long as it's lower if it's salty water. But this is a trivial amount of pressure. It won't support the internal shell. So the real interesting question is whether there are other dissolved volatiles in the ocean. If you could put enough CO2, you might be able to support the Mimas's shell at a lithostatic rate, but you have to pump in so much CO2 that it would actually start to precipitate out a CO2 clathrate. So that probably doesn't work, certainly not, it could contribute, but not in its entirety. And as Max also pointed out, the whole question of having an internal gas layer, whether this at all can be sustained due to, it would want to make its way to the surface pretty readily. I'll also point out that the CO2 inside Enceladus, this ocean, is very much lower than any kind of numbers that you would need to support the internal shell of Mimas. So in summary, small icy satellites that melt from within or undergo internal porosity collapse will generate shell compression. But if the icy satellite is small enough, it might actually resist this kind of shell failure and be self-supported because those stresses go as the radius of the body squared. This analysis, though, suggests to Paul and I that the Mimas shell is if the Lanier hypothesis is correct, would the stresses would be at least 6 MPa, and in fact we should see failure, and in fact should have failed. And we don't see any evidence of such compression. And basically, I think the whole idea about the young ocean and the cryptic compression that you can't really tell is there is kind of special pleading. I think some extra work, new work, could be done to understand the libration of a shell like Mimas, where the interior is not pressure coupled, but is only gravitationally coupled, as though there is a gap. I think that would allow us, in fact, then to assess that there is, in fact, a thicker shell on Mimas. Or maybe, as my last note, that maybe all of this is simply rubbish, and Mimas doesn't have an ocean. All right, thank you.
Okay, the next speaker is Paul Schenk. Mimas, John Bon Jovi-led rock song, in keeping with some of the poetic things. Constraints on possible ocean from topography and geology. So the title slides aren't up yet.
All right, well, Mimas seems to be undergoing an identity crisis. Can't decide whether it's an icy moon or an ocean world or a space station. We're going to look at it from the geologic point of view and see if there's any indication from the surface geology and the shape of whether or not there has been an ocean or is today. So obviously, if you look at Mimas versus Enceladus, shown to scale here, with similar lighting geometry, they couldn't be more different. Enceladus is very active. Mimas looks like a cratered lump of rock. The density is much lower, suggesting there's a lot lower radiogenic nuclides to provide heat and all that sort of stuff. But you couldn't be more wrong. So as previous speakers have mentioned, the high libration and periapse drift are what drives us to conclude, or the authors at least, to conclude that there has been an ocean sustained under the surface, presumably very young in any case. But anyway, so we're going to look at that. What does the geology tell us? Several papers in the past 2 years have said that there is no tectonic activity on Mimas, and I presume they mean current activity, and they're correct in that. But in the past, there has been, and that's why one of the things I wanted to talk to you about today is, first of all, we do have, thanks to the diligent efforts of people like Tillman and Paul and Candy and the other people on the Cassini team, we have global mapping, excellent global mapping for all 6 of the icy satellites of Saturn. And so the result is a global mosaic like this at about 200 meters per pixel, and with concurrent stereo, which allows us to do a shape model. And this is a shape model derived from stereophotogrammetric analysis, which is control point network, and stereo DM analysis with an additional layer thrown in for PC photochronometry, which means that the elevations are tied to the, and in this case, shown relative to the triaxial ellipsoid. This is a true shape model for Mimas, and we have those for all the other satellites as well now. A couple things I want to point out really quickly. Oh, sorry. Can I go backwards? It doesn't matter. Right, wrong button again. A couple of things I want to point out in the global map before I move on is that we have different terrain types. One is this area that has like a smoother texture to it, with punctuated by superposed craters, but it's very different from this kind of highlands terrain, which is deeply scoured and gouged by a much more intense cratering record, which suggests that there are areas on Mimas that have experienced some sort of either resurfacing or didn't have a strong cratering record. But you also see areas of chaotic terrain antipodal to the Big Herschel Basin, which we've seen pictures of. I'm not going to talk about that because it's not really relevant to the ocean idea, but you also have these elongate structures here which show up in the topography, which are of some interest to us directly because they relate to large troughs that we see on the surface. And looking at just the raw images, we see them self-evident structures like this, which start just east of Herschel and extend downward. This one's pretty degraded here, but you see the rim flank here, and there's a side flank there. This is a nice trough here. I also see this arcuate set here, very nicely expressed, even though it's highly oblique. You do see that there is a pretty good cratering record superposed on them, which suggests that they're sort of intermediate between ancient and Herschel. Herschel's relatively young, and I'll show a picture of that later. But it suggests a relatively intermediate age. These are not terribly recent, but we haven't done the crater analysis to get a precise age on them. It's very difficult to date linear features. If you look at them in map format, map projection, you see that there's a sort of pattern that's evident here of these arcuate trough systems. And these are negative relief features. These are not positive relief, as determined by stereo analysis. This one is particularly, it's really amazing to me that this sort of structure is taken late in the mission, so people didn't really recognize it till later. But it's parallel scarps and troughs, suggesting a sort of imbricate extensional trough system that has really pulled apart the crust in this area. The fact is that we see no positive relief structures here. We only see negative reliefs, which suggests that they're mostly extensional, not compressional. This is the map distribution of where they are. We haven't done a stress analysis on these yet, but it suggests that the east-west, the east-west tendency of these structures tends to support maybe either probably tidal deformation, but we haven't done the test on that yet. But the fact that they're mostly extensional suggests that that maybe we're dealing with global expansion. Let's turn now to the shape of Mimas and what the thermal history of the body has been. We now have, as I said, global shape models, true shape models for all 6 of the satellites, so we can do a comparative analysis of Mimas relative to those other bodies. And I talked a little bit about this last year. Mimas, which is the red curve here, this is a hypsogram, or basically a histogram of the elevations. And it shows the distribution of elevations relative to 0. And it's broader than Enceladus, which is the active body, by about a factor of 2. But all 5 of the inner bodies, inner satellites, are much narrower than the distribution of topography you see on Iapetus, which is much more rugged, and suggests that there's been a reduction, a significant reduction in topography on these bodies compared to what they would have had if they had been bombarded repeatedly by large impacts. That has been erased. That signature is just gone. If you look at the spherical harmonic coefficients of these maps, you see that they are indeed tightly distributed around near 0, which indicates that they're very close to triaxial, they're nominal triaxial spheroid shapes, except S2 is divergent here for Mimas, and that suggests that the tidal figure is displaced either due to internal variations or to a misalignment of the tidal figure with the IAU coordinate system, and that's exactly what happened on Enceladus, for example, in the recently released maps. So we see that. So we haven't really determined which of those it is. It doesn't really matter. But the resulting conclusion is that Mimas is a highly relaxed body, globally speaking, except for the preserved craters superposed on that, indicating there was an early thermal event which erased all the deep impact scars if they ever formed, because there's an alternative hypothesis that Mimas is very young. So there's that. Looking at individual craters, we see that there are indeed some shallow craters in the topographic record, these structures here. And you can actually, if you look closely, you can actually see remnant crater rims scattered around, which suggests that there are flattened craters there. But they're in an odd place. They're in a zone between the smoother plains, and they're actually quite close to the Herschel crater, which we see just off the edge of the disk here, so that they're within the Herschel ejecta deposit. And the craters, these remnant craters, are indeed heavily cratered themselves. So we're not really, there's no real way to determine whether these flattened craters are relaxed, buried by Herschel ejecta, or just simply pounded by repeated impact craters and ground down into a lower topographic state. So they're kind of inconclusive in terms of heat flow. But finally, we have Herschel itself, which is this very nice, well-preserved, extremely well-preserved crater. You see there's not very many superposed craters on it. It's relatively young. There's a unpublished report that maybe it's about 1 billion years or so, but that depends on your assumption on the model. But how much is this crater relaxed? Because it's an important constraint on the thermal history. It's so large and so deep, about 11 kilometers deep or so, that an ocean on Mimas almost certainly would have to relax it in some way because of the high heat flow. So the only way to really get at that is to look at smaller craters. And unfortunately, there's a large gap between Herschel and the next largest crater on Mimas. But you do you take the global shape model and the elevation map, and you do the work and count the craters and measure their depths, and you see the depth diameter curve. It has a slope of about 0.55, which is very similar to what we see on Tethys and Dione and Rhea. Those are published results by White et al. And the slope is consistent with Herschel being unrelaxed. In fact, if you take Herschel out of the fit, you get almost identical fit. You just cross off Herschel and just do a fit of these features and extend the line. It goes right through the Herschel point. Basically, it's undistinguishable. So Herschel is basically unrelaxed to the constraints that we have. So the conclusions are that we have a early global thermal event, which basically erased all the large impact scars that would have formed on a body of that size. We have a large global fracture network. Origin is uncertain, but they're almost certainly extensional, indicating global expansion. And then the shelling of the craters indicates that there's no recognizable signature of relaxation, all of which indicates that the geologic record is unconvincing as evidence of a surface ocean today, but there may have been one in the ancient past. So I just went 7 seconds over. Thank you.
Okay, thank you. The next speaker is, it's Bethany Furman, talking on polygonal craters on Mimas, potential evidence for subsurface deformation.
Hi, everyone. My name is Bethany Furman, and I've been working on this project throughout my internship while applying to grad schools. Today, I'm going to be talking about polygonal craters on Mimas and how they serve as potential evidence for subsurface deformation. So, as you guys have already heard a few times today, Mimas looks like it's geologically dormant because of its heavily cratered surface, but libration measurements revealed that it either has a non-hydrostatic core or a 3-layer structure with a core, an ocean, and an ice shell. Mimas's pericenter precession cast doubt on the idea of an elongated core and instead favored the ocean model. And other models of Mimas's orbital evolution revealed that its elliptical orbit is relatively new and its ocean's young. So most of the ocean moons that we know of typically have tectonic features at their surface. Enceladus and Europa are both in elliptical orbits that are maintained by orbital resonances, keeping their ice shells active and their oceans present. Mimas is also in an elliptical orbit, but over time its orbit's expected to circularize and its ocean should freeze. Enceladus is believed to be in a state of ocean freezing, and it's thought that ice shell thickening could have contributed to many of the extensional features at its surface. So if Mimas was also in a state of ocean freezing and ice shell thickening, we should theoretically see these extensional features at its surface. But if instead Mimas is in a state of ocean growth and ice shell thinning, we should theoretically see compressional features at its surface. In either case, these features begin their formation in the subsurface. So if Mimas's ocean truly is young, then we may not have had enough time to see these features appear at the surface. Also, if Mimas once had an ocean that has since frozen out, the extensional features left over should have been covered over by layers of impact ejecta, and those would also be in the subsurface. So if Mimas looked like a typical ocean moon, there'd be much less debate about its interior. But since it doesn't have the expected tectonic features, its surface geology is a main point of the debate. So we want to be able to use the surface features to better constrain Mimas's subsurface structure. Polygonal impact craters are craters that have straight rim segments, and they form because of tectonic features. They've been found on terrestrial and icy bodies across the solar system. They've been found to form as a result of compressional features like those on Mercury's large lobate scarps. And they've also been found to form as a result of extensional features like those on Dione's wispy terrain. They've been mapped nearby surface features, showing that their straight rim segments are typically parallel to the tectonic feature, although this is a current debate. And they've also been found in areas where there's no surface tectonic features, showing that they can reveal subsurface tectonic patterns. So a polygonal impact crater is formed when an impactor hits previously fractured target material. If an impactor hits structurally sound material, its shock can be dispersed in all directions, creating a circular impact crater. But if instead an impactor hits weakened or fractured target material, its shock should be redirected and creating a straight rim segment on the resulting crater. It's important to note, though, this diagram represents how a polygonal crater's straight rim segments can be formed during the excavation stage of crater formation, but it's also believed that these straight rim segments can be formed during the modification stage through wall slumping along the tectonic feature. So in this study, we mapped polygonal impact craters across the surface of Mimas in ArcGIS Pro. In the first step, we mapped any craters that had a straight rim segment using just the global base map, and this was done to avoid detection bias because the base map has nearly the same image resolution across the surface. In step 2, we used 11 higher resolution images from Cassini's narrow angle camera to verify the crater shapes. And in this step, we also excluded any craters whose straight rim segments seem to have been formed by external factors like overlapping craters. In step 3, we categorized all of the candidate polygonal craters according to their rim geometry and also noted their proximity to linear features or chasmata. And the chasmata locations were identified using the USGS map of Mimas with nomenclature. And the linear features were identified visually if they were prominent and visible in each raster that covered that area. In step 4, finally, we traced all of the straight rim segments and also calculated their orientations. These are the regions that we mapped on Mimas. The red cross hatching represents areas where shadowing or distortion made it too difficult to definitively classify craters. Regions A and B cover the leading hemisphere and the North Pole, and region C covers the trailing hemisphere. Here's an example of one of the rasters that we analyzed in this study. This specific raster is in the trailing hemisphere. As you can see, each of the identified craters were given 1 out of 3 categorizations, and these categorizations were made according to the crater's rim geometry and the definition of a polygonal crater. Although the definition of a polygonal crater is somewhat subjective, so we used the common definition of a polygonal crater, which calls for 2 straight rim segments that meet at a measurable angle. So any crater that followed this common definition and had typical polygonal geometry was categorized as a traditional polygonal crater. Any craters that didn't follow this common definition because they either had 1 straight rim segment or multiple that didn't meet at a measurable angle were categorized as segmented craters. And still, there were many craters left over that followed the common definition of a polygonal crater, but had atypical polygonal geometry. And so we called these unconventional polygonal craters. These were given a separate category so that if they're found to have a different formation mechanism, they can easily be removed from the data set. So in total, we found 88 craters with rim geometries that suggested their straight rim segments were formed by pre-existing faults or fractures. Of these craters, 24 are traditional polygonal craters, 20 are unconventional polygonal craters, and 44 are segmented craters. In total, there were 169 straight rim segments. One interesting result of this study that we found was that region C, the only region in the trailing hemisphere, had the highest surface density of polygonal craters, or of all of the crater categorizations. Okay. So of all of the straight rim segments, the orientations revealed a wide range of orientations, although notably less north-south alignments. Regions A, B, and C each showed unique prevalent orientations. And although we mapped the straight rim segments and calculated their orientations, we did not do the same for the linear features. So in the future, these can be compared with linear feature orientations in each region. Some of the identified craters were positioned on top of or close to chasmata and other linear features, although still the majority of the identified craters were at a distance from these features. From this, we can tell that most of the deformation is in the subsurface rather than the surface. So now we know how many polygonal craters there are, and we know that there's subsurface deformation. So to be able to determine how much subsurface deformation this is, we can compare with other Saturnian moons. Tethys and Dione both have tectonic features at their surface, and they also have polygonal craters. The polygonal craters that were mapped on Tethys and Dione fall under our category of a traditional polygonal crater. So we used the surface density of traditional polygonal craters on Mimas to compare with Tethys and Dione. And as you can see, Mimas has a lower surface density than Tethys and Dione. So now we know that Mimas has less tectonic features overall. So in conclusion, clearly Mimas has less tectonic features at its surface than Tethys and Dione. But now we also know because of surface densities that Mimas has less tectonic features in general than Tethys and Dione. Mimas may be our first example of a moon that's currently developing an ocean. And because of this, we don't know what surface expression to expect. So it's possible that the large number of segmented craters and unconventional polygonal craters could be indicative of developing tectonism. But still, there's more work that needs to be done. There's an opportunity to compare the orientations of linear features with the orientations of the straight rim segments. We also need to understand the formation mechanism of the polygonal crater straight rim segments. And finally, polygonal crater formation is poorly understood, specifically whether the straight rim segments should be parallel to or at an angle to the responsible fracture, and the number of straight rim segments that are expected for a crater. Thank you.
The next speaker is Mariano Blanco Rojas, and it is minimal relaxation of Herschel crater may be consistent with a young ocean on Mimas.
Well, hello, everybody. Thank you so much for being here. My name is Mariana Blanco Rojas. I am a second-year PhD student at Purdue University, and today I'm going to be talking about our approach to this question of Mimas as a potential ocean world and what we can learn about its interior from the evolution of its largest crater. So large-scale topography, in particular its formation and evolution, provides important insights into the interior structure of icy worlds. And with a diameter of 140 kilometers and depth ranging between 10 and 12 kilometers, Herschel crater, the largest crater on Mimas, provides really a compelling test for this young ocean hypothesis. Previous work done on Herschel's formation suggests that it formed on a very thick ice shell, likely ruling out the idea that Mimas had a substantial ocean at the time of this impact event, but not ruling out that it has an ocean today or developed one at some other point in its history. So what we do here is look at Herschel's evolution through time, in particular, the viscous relaxation of this crater, a process that over time will lessen the crater's relief and lead to it being shallower. Given that the relaxation process is highly dependent on ice viscosity, which itself is highly dependent with the temperature profile of the interior of icy worlds, we can use viscously relaxed topography to probe for the existence of an ocean, where the higher relaxation we see, the more relaxed these features are, the warmer and therefore weaker we can expect the interior of this world to be. The one issue here, and maybe it'll be a little bit clearer when I zoom into the crater, is that Herschel appears minimally relaxed, which for such a large crater in the presence of an ocean would be very, very surprising. So what we want to do here is model how long Herschel could potentially maintain its relief in the presence of an ocean, which may help us constrain how long the ocean could have potentially stuck around for, and if it even makes sense for us to believe that there's an ocean based on the topography that we see on the surface. So to do this, our work is guided by two key questions. How thick must Mimas's ice shell be for Herschel to remain unrelaxed for the 10 to 25 million years proposed as the longevity of this ocean from orbital evolution models? And what can Herschel's present-day relaxation state tell us about Mimas's near-surface temperature structure, which is traditionally indicative of near-surface porosity? For this, we perform numerical simulations using the finite element method and allow this crater to evolve over time, quantifying its relaxation. Given that the radius of Herschel roughly represents about 2/3 of Mimas's total radius, we used a 2D axisymmetric curved domain to more accurately model the large stress distribution and temperature profile of Mimas's entire ice shell. Our initial crater has a diameter of 140 kilometers and a depth of 11 kilometers. And as I mentioned before, we quantified the relaxation of this crater over a 25 million year old time frame. Our model uses a viscoelastic rheology where the viscous behavior is driven by both grain boundary sliding and dislocation creep. And we test a range of ice shell thicknesses consistent with libration measurements from 15 to 35 kilometers, where thinner shells necessarily imply higher heat fluxes. Finally, we also look at the effects of 3 different surface temperatures, 80, 100, and 120 Kelvin. And the reason why we do this is because on airless bodies, regolith will act essentially as an insulating blanket, lowering the thermal conductivity of the upper part of this shell and leading to higher temperatures at shallower depths. Previous work on crater relaxation, such as Bland et al. 2012 or McKinnon et al. 2023, has simulated porosity using these higher effective surface temperatures, which, as you can see in the plot on the slide, very closely resembles the thermal profile that you would get in the interior with the presence of that upper porous layer. So here we modeled for 2 higher than nominal surface temperatures for Mimas, 100 and 120 Kelvin, corresponding to between 35 and 50% porosity in the uppermost 1 kilometer of the ice shell. So moving on to some results, we begin by running a series of simulations using Mimas's nominal surface temperature of 80 Kelvin, and we find that in the absence of porosity, Herschel's modeled relaxation state after 25 million years is consistent with the morphology that we see on the surface. What this means is that if there is no porosity in Mimas's ice shell, our results suggest that minimal relaxation of Herschel is consistent with the presence of a young 25 million year old ocean on Mimas, even for the very thinnest ice shell thicknesses that we tested. Now, things get a little bit more complicated when we account for the effect of that upper porous layer that I talked about a few slides back. We find here that an effective surface temperature of 100 Kelvin will require an ice shell thicker than 25 kilometers to maintain Herschel's relief for 25 million years and be consistent with the ocean. So although it could be consistent with the idea of the young ocean, the ice shell would have to be thicker than those 25 kilometers. Now, the question here is, do we even expect Mimas to have any porosity in its shell? Well, given Mimas's small size and very low gravity, we do expect Mimas to have some level of non-negligible porosity, upwards of 50% in the upper few hundreds of meters to few kilometers of the ice shell. What this means is that even though the presence of a porous upper layer on Mimas's ice shell and an ocean could be consistent with the relaxation state of Herschel, it would be unlikely if the ice shell is thin. Now, aside from modeling the different ice shell thicknesses that would be consistent with this 25 million year old proposed ocean, our models also constrain the longevity of the proposed ocean for different ice shell thicknesses. The key takeaway here is that we find that for an effective surface temperature of 100 Kelvin, that those runs with the addition of the near surface porosity and a thin shell, Herschel will relax beyond observational limits in less than 25 million years. And those are the 3 runs that I've highlighted in gold on the slide. Notably, we find that for a 25 kilometer thick shell, Herschel will reach this limit in 25 million years. For a 20 kilometer thick shell, Herschel will reach and surpass this limit in only 4 million years. And for the thinnest shell that we tested, a 15 kilometer thick shell, Herschel will surpass this limit in only 33,000 years. Now, for higher ice shell porosity, the young ocean hypothesis almost completely falls apart and is no longer viable. We find that for an effective surface temperature of 120 Kelvin, consistent with the upper end of that 35 to 50% porosity in the upper 1 kilometer of the ice shelf that we tested, the ocean could only exist for a maximum of 1.2 million years based on Herschel's relaxation state. What this means, again, is that even though both porosity and an ocean could be consistent with Herschel's current relaxation state, it would be highly unlikely unless we somehow won the cosmic lottery and we're seeing Mimas just a few thousand years after its interior started melting. So what our results highlight here really is the significance of near-surface temperature variations. We find that a near-surface porous layer on Mimas will significantly speed up the relaxation of Herschel, and a potential way to test this in the future could be with a microwave radiometer, such as the one aboard the Juno spacecraft, which could be used to study those shallow temperature gradients and provide insights into the rate at which we could expect Herschel to relax, which combined with our models here could constrain how long this potential ocean could stick around for on Mimas. So just to wrap things up, our results suggest that minimal relaxation of Herschel crater is only consistent with a young ocean on Mimas if it has low near-surface porosity. Here we use the evolution of Herschel as a test for the existence and longevity of the ocean, and our results suggest that an unrelaxed Herschel could potentially be consistent with the young ocean, an ocean that is younger than 25 million years, if the ice shell has low porosity and is thicker than 25 million years. And in future work, we hope to incorporate a time variable ice shell thickness as proposed by orbital evolution models and also a larger parameter space. Thank you so much, and I look forward to your questions.
Would all speakers please return to the stage? Including you. Okay, first question from Aaron Leonard. Please say your name and affiliation and who you are asking a question for.
Great, thanks. Aaron Leonard, JPL. This was another really great set of talks, so I just wanted to thank all the speakers because it was really fun to watch you all talk about Mimas. But my question is for Paul. Paul, you mapped out some really nice looking east-west structures that I thought were really interesting, and then you stated that you thought these were due to global expansion, potential thickening, and I was wondering why that doesn't follow for me, right? A global expansion would probably generate features in all sorts of directions. So can you just explain that a little more?
No.
Okay.
No, I tried to state, and I think I did, that we haven't actually done the stress analysis. So we don't really know what the stress model fits that particular pattern. It's a little odd that they're east-west, and some bodies we do see that orientation, like on Tethys, but it's not east-west. It's sort of like in a great circle. So yeah, maybe I shouldn't have said that, but anyway, the fact that they're almost all extensional and they have this sort of imbricate structure does suggest some sort of expansion, at least. What the overriding global stress field is unknown.
Great, thanks.
Hi, this is Dave Minton from Purdue University. I also have a question for Paul, and it's also about that same set of features. So they, to me, superficially resemble the equatorial graben on Vesta, and combined with that sort of smooth plain to the north, the way you mapped it out, it kind of reminds me of the situation at Vesta where you have the Rea Silvia and Venenea basins on the pole, and these equatorial graben that actually come from the impact process, which Tim Bowling modeled back at Purdue a long time ago. I'm just wondering can you rule that out, or is that a possibility that these aren't actually some sort of tectonic features from angiogenic process, but just the result of some really big basin that's been relaxed away to almost nothing?
Yeah, you have to sort of look at the stratigraphy there. The troughs, as I said, have a sort of intermediate age. They don't look ancient, but they don't look young. Whereas the erasure of any large structure that formed before then is gone. So it's probably older than the troughs, if there was any structure there. That's the problem with remote sensing, is that we don't have boots on the ground to actually date these things. But yeah, there's no prima facie evidence for anything like that. We don't see any radial scouring or anything like that, anything coming from the other side. So I would tend to rule that out. I mean, you can't be absolute, but yeah.
I'd like to say interject just to remind everyone, Mimas has a reasonably high eccentricity today and could have had a larger one in the past and could have actually undergone a great deal of tidal retreat, especially if it's a ring moon. So there are a number of potential stress sources that could lead to orientation of these extensional features on Mimas's surface. And one other comment is that we look at Tethys and we look at Ithaca Chasma, and it is oriented, and it's often described, and when it goes back to Voyager days, as being due to the freezing of an internal ocean. But because it started to form, it sort of took up the stress and the way the whole shell fractured. At least that's the idea.
Question.
Brandon Johnson, Purdue University. I think this one's for Bill. So this session has me kind of believing that Mimas probably doesn't have an ocean, but then the question is, how do you explain the physical vibrations and the astrometry? What is there a problem there, or is there some other explanation? Have you thought about that?
Well, as other speakers have mentioned, the original anomalously large libration of Mimas, another explanation was that it had an internal density distribution that just basically a denser material that drove that. But then the so-called negative periapsis drift that Laney et al. Reported seems to require an actual ocean. Now, if you look in detail at their paper, they don't necessarily, on that basis alone, require a thin shell. They can have a thicker shell. It's the libration that is driving the inference of a thin shell. So one possibility that I've thought of is that we do have a gap and there's vapor down there, and that the shell is free to librate more, and it's actually thicker, and it's thick enough that it doesn't necessarily fail, and all these other things go on. I mean, I don't necessarily believe it, but that's one possibility. Or there's something odd. I cannot tell personally, looking at, we can't interrogate this periapsis drift data. It's astrometry. It's very, very tricky stuff. You simply have to accept that they did the right thing.
Okay, thanks.
Yeah.
Hi, you guys. Shelby Osborne from University of Arkansas Center for Space and Planetary Sciences. I have a general question for anybody who might have some expertise on this. It was mentioned in Bethany's talk that much of the surface deformation of these icy moons comes from internal forces, not external. And I was just wondering what you guys thought about that with like Enceladus and the strange spatial distribution frequency of the craters. Do you guys think there's like some percolation effects going on that are more internal, that are affecting the outer surface of Enceladus, or do you think it's all just craters? Sorry, all my questions are really creative and strange. That's why I was asking all you guys.
So I might have misspoke. When I said that about the deformation being in the subsurface, I meant that there was more subsurface deformation than surface deformation, not necessarily that it's coming from the subsurface.
Oh, okay, I see.
Yeah, I don't know much about Enceladus. So.
Okay, that's all right. I'll find you after the talk and we'll talk about it. Thank you. Hi. I'm going to use that one. Hi, Alyssa Roden, Southwest Research Institute. First, I just wanted to thank everybody for talking about Mimas. It's really exciting. So my question is for Mariana, who unfortunately is behind the podium. Hi.
So first off, I did see it in your final slide. I just wanted to clarify that in the evolution that's 10 to 25 million years, Mimas spends very little time with a very thin shell. It starts at 70 kilometers thick and then is thinning through time. And I'm happy to share with you, if it's helpful, what the heat flow through the surface would be throughout that whole evolution. But my guess is that even your worst case scenarios may be consistent with an ocean because it's just not been there that long and the ice shell hasn't been thin that long. But my question is whether you've considered starting with even deeper Herschels to see whether the present day morphology is consistent with some amount of relaxation.
Is this on? I think it's on. Yeah. Okay. Yes, for sure. So one of the things that we want to test with that larger parameter space that we want to test out later on in the project is deeper Herschels. So we are going to account for the idea that maybe the present morphology that we see, the present depth of Herschel, could be a relaxed state and start from there. And we will also be looking to model that thinning ice shell through time. So yeah, we're going to account for both of those scenarios during the final project. But yeah, you can definitely see how with this consistent thickness, the results that we would get with the addition of porosity would not be consistent with that ocean. But we're definitely going to account for that before the final paper is published.
Great, thank you.
And I'll add to that I think that's a valuable thing to do, but from the observational constraints from the depth diameters of the smaller craters, which I took the freshest craters, I forgot to mention that those are freshest craters of those sizes that we could find on the topographic map, indicates that Herschel is probably not much deeper than it is today. You would have to have a curve that goes up like that, and that's not seen in nature. So
Right,
it's unlikely, but it's a good thing to place constraints on the process.
Thank you.
Hi, Simon Captain-Horn, University of Hawaii at Hilo. My question is for Bill. I think I'm going to be dreaming about Dyson satellites tonight, but this is kind of like a series of hypotheticals. So if you have a gap between the shell and the ocean, is it possible that you're removing the tidal forcing on the shell so you can just switch off your tidal forcing? And then if so, wouldn't you just have compressive stresses due to the, from the thinning, which would be isotropic, which would take away all shear stress? So how would the compressive deformation occur in that kind of circumstance?
Well, the compression in the shell is due to it wants to fall in, but it can't. So it's like a Roman arch, but now it's a Roman sphere. So it's different from a Dyson sphere, I guess. But it's still subjected to, tidal forcing. So it will still bend and flex as in, due to Enceladus's eccentric orbit. And I didn't even mention it, but you're going to have very high tidal stresses in the Laniadol shell. Whether there's an ocean there or a gap, because it's Enceladus. I mean, Mimas's eccentricity is 4 times higher than Enceladus. It's closer to Saturn, and tidal. So the forcing goes as 1/r cubed, and the love number H2 is also likely to be larger just because of Mimas's structure.
So the shell would continue to tidally respond even without the ocean
Yes.
being in contact.
Oh yeah, oh yeah. The ocean, it would respond more because it's only gravitationally coupled in this fantastic concept of a gap.
Okay, very interesting. Thank you.
Hi, Sierra Ferguson, Southwest Research Institute. My question is for Paul. So I noticed that your smooth plains unit is mostly concentrated near the North Pole. Some of my crater concepts suggested that this is one of the older areas on Mimas. And so my question then is, how would a potential older age change your interpretation for that smooth plains unit?
I would want to talk to you about that for sure, and see the crater counts and the density distributions and see what they look like for the rest of the satellite as well.
Yeah.
I'm basing that strictly on the topographic record, which is based on looking at Tethys and Downey Tethys and Downey as well, where you see deep gouges from the really old craters that have been beaten up and creates this kind of thing. Whereas this is kind of flat with a couple craters on top of it. So granted, it's not the highest resolution that we got in the Cassini mission. So there are limitations, but that's what it's based on, is strictly on the
topographic interpretation.
Cool.
So yeah, we should talk.
I'd love to.
Sarah, don't go away yet. Because I'm going to take a prerogative and ask you a question.
Okay.
So about the age of Herschel from your crater counts and maybe the new calibration of Nesvorny et al. I don't know. Do you have an estimate that you share with us?
So I have not run rerun my crater counts with updates from David's model or Bill's model yet. That's something I'm wanting to do, but I know at least Bill Baki's new models still say that Mimas itself should be old, but I still want to work with Bill to run my counts through what he's been doing for that.
Okay, thank you.
And we, like, based on the other counts that we had across Mimas, we do see that Herschel is likely the youngest and is about 10% the age of the other non-Herschel related terrains that I mapped.
Okay.
We haven't got very
And Basin.
we haven't got very long left, so try to keep your questions short so we can accommodate all four. Thank you.
All right. Hello, Janie Levin from Brown University. My question's for Mariana. I was wondering if you had thought about how various compositions of your Mimas could maybe help your Herschel crater stick around for longer, since ice rheology gets really weird really quickly.
Yes. So far we have not considered other compositions other than pure water ice. All of our models are being run with pure water ice. We think that although this could be affecting the relaxation of Herschel, probably porosity in the near surface or even deeper into the ice shell has much more of an effect. So that's what we decided to test, but we'll definitely look into that once we keep going on with the project.
Thank you.
Two on the left, and then Alyssa if there's time. Sorry.
All right. I feel like I have like 5 million questions, but I'll start with one. So for the last speaker, first off, I really like the zoom out from the finite element model slide transition. Perfect. Beautiful. And then an actual question. So years and years back, people looked at the thermal inertia of Mimas and they saw it was different where Herschel crater was compared to the rest of Mimas, which could speak to a difference in the porosity. It would probably be closer to the surface that it's actually telling us anything about, but it could mean something about the deeper crater as well. And I'm also thinking about earlier talks in the impact cratering session where impacts can either generate or destroy porosity depending on what the pre-existing porosity condition was. So I guess, have you considered if the porosity within Herschel crater can be different from the porosity elsewhere, and how would that affect your model?
Yes, we have thought about this. We would expect there to be a higher level of porosity near Herschel just because of that impact-induced porosity that you mentioned. We haven't looked extensively into the porosity of Mimas before the impact of Herschel, so we would have to look into how that initial porosity is affected by the impact itself. But the key thing to keep in mind is that if we have more porosity at a lower depth, we will see Herschel relaxing faster. So even if we have moderate porosity as the models show, we will have a much quicker relaxation of Herschel. And there's definitely some porosity near Herschel. So.
And I do remember those results, and they're specific to the floor of Herschel, which suggests that if it is young, it has some sort of impact deposit. Probably not melt, but some sort of breccia or something like that, which could either increase the porosity or decrease it depending on how you interpret impact floor formation. But yeah, that is definitely a good point worth considering.
Thank you both.
Yep, there's time for one more.
Noah Hammond, Providence College. I guess I was going to ask a question of Bill. Maybe it's more of just a random idea for this, for the one where you have porosity closure and you get a gap rather than an ocean. I wonder if there's a middle ground there where instead of developing a gap, you just get a zone of like low pressure where then you could get really easy like frictional failure. And is that a way to decouple the interior?
Yes. Yes.
Good answer.
Actually, I think we can therefore accommodate Alyssa's question. Sorry, I didn't think it would be that quick.
Okay. Hi. So Alyssa Roden, Southwest Research Institute. My question is for Bill. So first off, I just wanted to say we did calculate tidal stresses throughout the evolutions of those thinning ice shells in the 2024 paper, and they're still only hundreds of kilopascals. So the tidal stresses will not dominate over the compressive stresses, even with higher eccentricities. But my question is, it seems like you've made an assumption in your study that if you have compressive failure, you will have surface features. Is it possible that the compressive failure begins in the subsurface, and so the surface manifestation is simply not as obvious or perhaps more diffuse?
That's an interesting point. So if you can imagine either viscous creep at the base of the worm, if the shell is, at the melting temperature, the base, or compressive failure at depth, where in fact the stresses are somewhat higher, but only on 10%. But all that will do is transfer the overall load to the remaining elastic part. So you're just going to jack up the remaining stress in the remaining, if you like, elastic core.
I see. So you wouldn't expect, say, subtle folding like we see on Europa. You're looking for a peaky ridge thing.
Well, I would predict shear failure, but can we hide it through compression of porosity? Can we hide it through folding? Can we hide it through a myriad number of small sub-resolution faults? You can wave your arms and do that.
Sounds like we need a mission.
Yeah.
Thanks.
Thank you. Okay, thank you, panelists. If you wouldn't mind getting off the stage, we would like to go to the next session. Okay, the next speaker is Robert Tyler, speaking to ocean worlds maintained by ocean tidal heat expected on several Uranian moons. And Robert Tyler's remote. Robert, can you test your voice, please?
Yes, I can test my voice.
Perfect. Okay, go ahead.
Well, thanks for everybody for coming. I had planned on coming myself, but maybe you can see by my affiliation why I'm not there. Something came up. I want to talk about ocean worlds maintained by ocean tidal heat expected on several Uranian moons. Expected by me, at least. Next slide, please. So for a future Uranus mission, the prevailing view seems to be that the likelihood of finding oceans is highest on the larger moons, Titania and Oberon, and much less likely on the smaller, Miranda, Ariel, and Umbriel. What's that based on? It's based on the recognition of the larger integrated radiogenic heat. Well, the two larger moons, they have more surface to volume ratio is working for them. They have more integrated, fluxes of radiogenic heat through the seafloor. That makes no problem there, makes sense. But it's also based on the erroneous claim that the ocean tidal heating is weak. I don't agree with that at all. The reason why I think it's erroneous is that it's based on the incorrect assumption that resonant or enhanced tidal heating requires very thin oceans. And that's despite multiple published contrary examples where you can have strong tidal heating even in thick oceans. So my view is essentially the opposite, and it's based on solutions of the complete fluid dynamic equations. So my background, initially was physical oceanography from Earth, and now I'm out in since the last 15 years or so out in the planetary context. Next slide, please. So this kind of busy plot here is it's a diagram of the tidal power or the heating rate as a function of the ocean thickness and dissipation timescales, or at least I've translated it to those two parameters. So what do we do? It's very important to sample all of the solution domain before coming up with any claims, because with fluids, there's resonances and other situations where the tidal response can be orders of magnitude different if you change the parameters. So it's very sensitive to the parameters. The reason why the ocean thickness is important is the adjustment scales of the fluid tend to scale with that. In the simplest example, it would be the square root of GH that people might know, and the H is the ocean depth. And so whether there is resonance depends a lot on whether the ocean can how its time scale for adjusting compares to that of the forcing. And the x-axis is I've translated that into Q, or the quality factor or tidal parameter. What Q really is a non-dimensional dissipation time scale. So, Q doesn't have a monotonic relationship with the total amount of dissipation. It's just the time scale. The amount of dissipation also depends on the stored energy in the tidal response. So in this busy plot, first just notice the huge differences in color. This is a log 10 scale. And we have orders of magnitude difference in the amount of tidal heat generated depending on what those two input parameters are. I've also plotted on there a black line describing the radiogenic. This is for the example of Miranda, and I did it for all the moons, but I'll just talk about Miranda here. And there, basically everywhere that is, greener or redder than light blue, we have the situation where the ocean tides generate more heat than radiogenic. And also you can see that in most of the plausible scenarios show tidal heat exceeding radiogenic. So ocean tidal heat can easily explain far more heat than radiogenic, and it can explain enough heat to basically support the ocean. So these configurations are not only possible, but I think that they are also inevitable if you don't have other heat sources, because the ocean will essentially freeze down into one of those configurations. And that's what I'm going to try to explain in the next slide, please. So that's just a blow up of a section of that. So the blue lines are the depths of Miranda's ocean that I've actually put over the top of there. Those are in kilometers. So we have everything from like the lowest blue horizontal line is like 1 kilometer, and then we have the full ice-free situation. So if you imagine an ocean being born in an initial ice-free ocean, this is for Miranda, so that would be the white dot at the top. The mistaken view is that to get to one of the resonant situations or the high heat situations, you would be going straight down in the diagram, and you'd have to go all the way down to the ocean depth where your ocean is less than 1 kilometer thick before you would experience those high energies. And I'm very confident that is incorrect, since it's been shown. I showed it in 2014 already, but here I'm making the argument that that's not a realistic assumption, because as you try to freeze the ocean, you are also accumulating ice, and the damping time scale should change. In other words, Q should change, and you should have to veer left as you move down. So it's you won't go all the way down to the resonance as seen by the red curve, but it'd be something like the green curve where you must be moving off. And as you get to that white curve that I've drawn, you have a balance where, at least for a conductive heat shell, you would have a balance with it where that's where it would equilibrate. So an ocean being born at the top white dot would move off towards the left to one of the dots, as you see and indicated there, and it would not require the ocean freezing down to a small depth. So if you can see the white line there, you can see that basically there's all kinds of intersection points, but the ones I'm talking about where the dissipation timescale, or Q, would move to the left, well, you must be intercepting that white curve at a much thicker ocean. Next slide, please. All right, so these are just the conclusions. This study shows that the smaller moons Miranda, Ariel, and Umbriel are the most viable candidates and should support thick oceans through the process of self-tuned resonance. So the self-tuned resonance is basically, if there's no other heat sources supporting the ocean, it must freeze down toward the bottom of that diagram we were looking to, because that would be the situation of a frozen ocean is all the way at the bottom. But then the process of freezing pushes it into a higher tidal heat state, and that stabilizes it. And the argument here is that these results can explain observations of the surface geology and heat flux on the inner moons that implicate heating values exceeding 25 milliwatts per meter squared. If we can move for a second just back to the previous slide. You can see off, kind of on the left side, the contours for 25, 50, and 75 milliwatts that I've also imprinted on there. And I think that the real situation will be one of the dashed red lines, where you would be born, at the top, and you would intersect at an ocean would be much thicker than the ice shell thickness is what I come up with when I start doing additional calculations. But the first part is that you can't freeze the ocean without first pushing it into a high heat generation state is the very robust conclusion. Thank you.
Okay, we'll have a very brief pause before the next speaker. We have a minute before they start.
I would say in that minute that I was very interested in Mimas because I've written before that I can't understand why it wouldn't have an ocean since it would be, for the same reason as self-tuned resonance.
Very cool. Okay, I will take a few seconds to introduce the next speaker. The next speaker is Scott King with his talk, Fit to be Tried, a prequel to a machine learning study of Ariel's interior. I'll say go at the moment that the people are expected to be in the room. I've got a few seconds left. Don't think people are wondering. Okay, go.
All right. Thank you for sticking around this afternoon, and would like to talk to you about some possibilities that we see. In fact, you have mostly heard about tidal heating, but I'm going to show you that radiogenic heating can actually produce some rather interesting results. Our sort of long-term goal here is to create a model that we can use to understand icy moons. We decided to start small, and we started with Ariel. And this is based on a neural network framework that my friends at DLR have published specifically for Mars modeling. And they've been able to show that with enough forward models from convection modeling, that they're able to do 2D and 1D models and predict very well with their neural network what they expect the internal temperature through time to be. And so I said, well, gee, could we take this neural network and try this for icy bodies? And because we're looking at low degree structure, I decided to, push them a little bit and say, could we do this also in 3D? And so we decided to pick Ariel. I don't need to tell all of you what's going on in this moon, but essentially because it's roughly equal parts of rock and some sort of volatile, presumably mostly water ice, but potentially other volatile, we looked at this from the point of view of saying, if we segregate the rock into the radiogenic elements into the rock, and we have a uniform, heated sphere from below, what can we say about what's going on in the surface? So unfortunately, when you think about modeling interiors, as you all know, we know very little. We're assuming that we know the radius of Ariel. We're assuming that we know the mass of Ariel. We're assuming that we have a chondritic composition for what we call the rock component. And we're assuming that water ice dominates the rheology of what's going on. Small bodies, I come from a world thinking about Earth and Venus and Mars. Small bodies start out with very little primordial heat, right? There's not very much energy to heat these things up to begin with. So unlike what I'm used to thinking of, starting with the magma ocean and cooling down, we're thinking of a body that actually the radiogenic heating causes this thing to heat up at a certain point. We're modeling what's going on in the volatile shell and using a 3D thermal evolution model. We basically have the constraints and rheologies and equations of state that most people use for modeling these things. And what I want to point out is we have 400 models, which is not nearly enough, but it was enough to actually get us moving. And we varied with Gaussian variability, the ice rock boundary radius, the ice density, the pre-exponential of the viscosity, which we're taking as a proxy for some sort of stiffening component in the ice, initial temperature, and so forth. I'll show you what one model looks like because otherwise it's not very interesting. But through time, 4.5 billion years, the mean temperature in the ice layer decreases somewhat. We go through a initially conductive phase. It becomes convective. There's a velocity, I think that's scaled probably about a factor of 10 too big, that decays with time, and the solution, the one isosurface of the solution looks something like this through time. It's a tetragonal pattern, and then it basically becomes conductive. Right. Now, the gold temperatures here, this is the temperature at the ice rock boundary. My muscle memory wants to say core mantle boundary, but that's not particularly helpful in this case. The gold temperatures are above the melting temperature of water, and we're not dealing with the thermodynamics of melting here. So essentially assume that everything here, unless you get up to like 79 degrees above that melting temperature, that everything here is slush causing this thing to melt near the core mantle boundary. This is what temperature is doing through time. When we start looking at all these things together, I'm an old guy, I don't trust machine learning. And so I wanted to say, what could we see for ourselves? You're going to see a number of plots like the four that you see here. On the vertical axis, in this case, we see diffusion start time. In other words, when did the model go from convection to diffusion? You're going to see core radius, initial temperature, viscosity, and temperature through the entire model. You can see that there's one parameter right here, the ice rock boundary radius, that actually correlates very well with when this thing goes from diffusion to conduction. If we look at things that maybe people here are interested in, when does this thing start to melt at the base of the model? It's a little bit, this one is where we can really use machine learning to put together what the proper perspective of these parameters are. But what's interesting here is that below a viscosity of around 10 to the 14th or so, or close to 10 to the 15th, we never see an ocean. Essentially, the shell is soft enough that what actually happens, there's enough advection of heat that you never actually need to melt, which was sort of a revelation to me. If you look at how long an ocean might last, there's a very strong correlation between viscosity and ocean lifetime. Notice in none of these calculations does the ocean actually last until present day. So my takeaway from this is, even from this relatively simple suite of calculations where we only varied a few things, we can learn an awful lot. But there's an awful lot more that we can do with these calculations. We can look at the pattern of the material. We can look at surface deformation, because those are things that might be more interesting to people who are designing missions as opposed to convection and fluid dynamics people like myself. We can look at the thickness of the lithosphere. We can look at the surface heat flow. We can predict moment of inertia in K2, things like that, that are actually relevant to what people are doing. So there's a lot more that we can mine out of this. We haven't yet included the thermodynamics of melting. I was astounded at how much we were actually able to pull out of this just by looking at it without turning to the black box of machine learning. And we'd really like to see broadening this approach to look at other icy bodies. Thank you.
Okay, our next speakers, Cochrane, Vance, and Raymond, characterizing Ariel's possible subsurface ocean using magnetic observations from a multi-flyby Uranus mission concept. And Corey Cochrane will give the talk.
Oops, 1 second. Oops. Sorry, I have to, there we go. Okay, thank you. So yeah, again, my name is Corey Cochrane from the Jet Propulsion Laboratory. Basically, I'm going to be presenting an uncertainty quantification analysis of a possible subsurface ocean within Ariel. And I do apologize to the geologists in the group. This is, in fact, not a picture of Ariel. We don't have complete coverage, so I figured this image would suffice. Okay, so I think most of us are familiar with the fact that the reason we know there are subsurface oceans in the solar system is from the magnetometer measurements made from the Galileo mission. Here are the magnetometer measurements made from Callisto and Europa. And as we can see in each one of the magnetometer components, a little blip in each one of these signals. This is attributed to a magnetic induction response from a subsurface ocean. The Galileo team, led by Margie Kivelson, essentially determined that these signals were synchronized with the rotation rate of Jupiter, ruling out a permanent internal dynamo. And basically what this means is that when you fly by a different time, here at C9 pass and E14, the phase of this signal effectively changes. So this is a good indicator that you have a subsurface conductive layer within Europa and Callisto. So what is this source of the AC field? So magnetic induction is facilitated by time-varying magnetic fields. You have a time-varying magnetic field. It's associated with an electric field. And this electric field drives electrical current within a conductive layer and induces a secondary magnetic field that can be measured by a magnetometer. For the Jovian system, we see this tilt of 9.6 degrees, and the ice giants of Uranus and Neptune, 59 degrees and 47 degrees tilt with respect to the magnetic axis with respect to the spin axis. And essentially, this causes time variations in the magnetic field as the planet rotates in the observation frame of the moons, mainly because the moon will see different magnetic latitudes. So what happens? So this is just a simulation of Uranus rotating, and we have 3 of the moons shown here, the inner 3 moons. But I want to focus on Ariel real quick. And if you look at the magnetic field being traced out over here in this middle plot, essentially this is it looks almost purely periodic. However, if you were to take the Fourier transform of this signal or any of these other signals, you would see that it's a lot more complex than this. There's other tones buried in this time series. And this is due to the orbital periods due to the moons, and also the beat frequencies between these 2 fundamental periods, as well as their harmonics. So rather than explain the math and the physics behind magnetic induction, I figured I'd just show you what it looks like instead. Uranus is a really complicated system. So for starters, first of all, I rotated Uranus so that its spin axis is pointing up. So we can see the moon orbiting in this fashion. Here we can see the magnetic induction response from a possible subsurface ocean. Here just simulated with a perfect conductor. And as you can see, the rotation of this magnetic dipole essentially from the ocean. And it's this rotation of the magnetic dipole that allows us to distinguish it between a permanent internal dynamo. And if we look off to the right, this is the same figure, except for now we're simulating the total field, Uranus's field plus the induced field. And because the ocean acts as an electromagnetic obstacle, effectively these magnetic field lines cannot pass directly through the ocean. They get perturbed, as you can see here. They kind of bend similar to the way water flows around a rock in the water. Okay, so we use the flyby concept that it contains 8 close flybys of Ariel, all within 100 kilometers. And we have really good Uranus longitude covered, which is really important. So one of the main questions we get asked is how do you actually map magnetic measurements in units of nanotesla to internal parameters of the moon? And I don't know if you saw, but yesterday we were given a presentation by Scott Chang, who introduced this software called Planet Profile, developed by Steve Vance, which allows us to effectively model the induction response for tens of thousands of different oceans. And what we do is we actually forward model what's called the complex response function. And this complex response function tells us the scale factors and the phase delays associated with the driving fields at the different frequencies. Here, I'm just plotting the synodic. So in the complex plane, we have a cosine of the phase delay, and here is a sine on the y-axis. And this gives us a two-dimensional space to use for classification. We model tens of thousands models. We do the forward modeling. And then when we get actually measurements, we can do the inversion across all the flybys when we stitch the data together. And we actually do a Monte Carlo simulation where we randomize the noise sources for 1,000 different tours. So essentially, we can get a bunch of different answers, not just a single answer, and look at the distribution and get better constraints on our interior estimation. So we basically picked one particular ocean to see how well we could recover it amongst the tens of thousands of possible combinations that are possible. Here we took an ocean from the work by Julie Castillo, really deep, really thick ice shell because these moons are a lot colder, about 150 kilometers, an ocean thickness of 30 kilometers, and an ocean conductivity of about 15 Siemens per meter. So the first thing we want to do is before we can actually model or assess the interior properties from the induction signal, we have to take care of the planetary field. So what we do is we do an inverse method where we estimate 3 different frequencies. Here we do the synodic, the second harmonic, and the third harmonic. We estimate the in-phase and the out-of-phase coefficients for these. And then we can, what I'm doing over here is plotting the errors for each one of the components, Bx, By, and Bz for the 3 frequencies. And they're color-coded associated to the flyby. So it shows you how many flybys you need to converge onto a good answer. And here, this is representative of the errors. So what we want to see is we want to see a small variance and a good accuracy. So right centered on 0. And as you can see, after 8 flybys, we get really good characterization of Uranus's magnetic field that drives induction. Moving on to the induction field. So once we have the planetary field, we can subtract that from the total field, and we're left with the residual up here on the top left. And this, we take this data and we do a second stage inversion where we're able to again invert for the complex response function. Here shown the error in the in-phase and out-of-phase components. And as you can see, we see this nice tight bullseye here in the synodic period. And the reason we see that converge so fast is because the signals, the driving field is about 10 times as strong as the second harmonic and the third harmonics. And you can see it takes a lot more flybys for these other harmonics to converge. Okay, so now that we have estimated every single one of these Monte Carlo runs, what we can do is we can project these data points, these estimates, into our classification space. Here is just the synodic, but this is actually a hyperdimensional space. You can use many frequencies you want. We're actually using 2 frequencies here, and there's 2 components for each frequency, meaning that it's a 4-dimensional space. We're actually using just 2 are shown here, though. And what we do is we actually take every one of these Monte Carlo runs, and we search basically the database to see which ones are of the forward models are within 1 nanotesla of these Monte Carlo runs, and then we can plot them as magenta dots in these plots over here in a display that we're all more comfortable looking at, the ocean conductivity model space versus the ocean thickness, and the ice shell thickness versus the ocean thickness. Okay, so here are these plots again. So again, the plots in magenta are basically indistinguishably from one another based upon the noise model that we introduced to it. So this basically says, this first plot is that, so the black dot is a representative ocean, 30 kilometers thick and 15 Siemens per meter with conductivity. The black dot is indistinguishable from those magenta dots. But as you can see, we can't really place tight constraints on this simply using the magnetic induction data. But again, this is a three-dimensional space. So if we were to rotate it and look at the ice shell thickness versus ocean thickness, we can see this nice horizontal line in this space. And this is great for characterization, which means that we can actually characterize the ice shell really well, plus or minus 15 kilometers using magnetic induction alone. Now, we don't get the hydrosphere's thickness because we don't know the ocean thickness from this plot up over here to the left. But just as a introductory to the next slide will be given by Flavio Petrica, the gravity, the static gravity measurements will be able to help get the hydrosphere thickness. And if we can constrain that to plus or minus 30 kilometers for aerial, we can significantly constrain the ocean thickness. Using that same constraint for the bottom plot, in order to try to see what we can get with the conductivity, it turns out that we can't do too much. The space is the same, basically. And the reason for this is because although people think Uranus is really complicated, the magnetic field, in the frame of reference of the moons, you're actually only getting one frequency, dominant frequency of induction, unlike Europa, where you get the orbital period, which is very valuable. So two frequencies is very important. But with that said, that's all I have. And I'll glad to be taking any questions you guys have them.
Okay. Okay, well, we will follow then with the final talk of the session by Patrica Orlando, Melwani Del Swani, and Castillo Roger, Gravity and Radio Science Investigation at the Moons of Uranus to reveal subsurface oceans and characterize internal structure. And Flavio Petrica will give the talk.
Hello, everyone. My name is Flavio Petrica, and I am a postdoc at JPL. Today, I'm going to show you some of the efforts we're doing at JPL for the early formulation of the gravity and radio science investigation at the moons of Uranus with the Uranus orbiter and probe. So Uranus has 5 large and regular moons, which are very interesting and very different from what we learned at the Jupiter and Saturn system in the last few decades. So these moons are in a very particular configuration. As you can see here, they have very similar physical properties in pairs. So you can see in the center, Ariel and Umbria, there are very similar radius and mean density. And that applies also to the outermost moons, Titania and Oberon, that are very similar, again, radius and mass. And then there's a smaller moon, a much smaller moon, which is the innermost one, Miranda, which has much lower radius and much lower mean density. We don't currently understand why these moons are in this particular configuration, but gravity science can help us understand why these moons achieve this particular configuration. In addition to that, we can use gravity measurements to understand, for example, the composition of the rock interior of the moons, understanding what these moons are made of at present day. And we can also, gravity measurements can also help in detecting subsurface oceans, understanding whether these moons preserved subsurface oceans from freezing. So starting with these questions, we wanted to understand which kind of measurements we need from gravity and geodesy to detect subsurface oceans and study the interior structures of these moons. So the primary measurements from gravity and geodesy that we can use to detect oceans are the response to gravitational tides and to force vibration. Both these geophysical processes depend on the pull from the central planet, from Uranus, and they are significantly increased by the presence of the subsurface ocean. So if we are able to detect a large tidal response or a large response to the force vibrations, we will be able to tell whether these moons host a subsurface ocean or not. And so we modeled the interior structure of the moons in order to understand which kind of precision we need. And then we use these to simulate the gravity and radio science investigation based on some of the mission design efforts that we're doing at JPL in order to narrow down requirements on the trajectory design and on the instrument that we need. So we start with the interior model. We modeled all the moons as 3-layer bodies accounting for a rocky core, an ocean, and an ice shell on top. And all the properties that influence the measurements that we want to make, we varied them in a Markov chain Monte Carlo framework, which is a nice way to do this because it allows us to build models that are consistent with the few observations that we have, the mass and the radius, and also to explore a broad parameter space, and so to combine many different values of the interior properties, and so simulate many different interior configurations for these moons. So including unlikely configurations that we might find at the moon. And so this is an example of a result that we can get with the Markov chain Monte Carlo approach. If you look at these histograms, they represent the tidal lobe number K2 that quantifies the tidal response of the moon. So the larger the lobe number K2, the larger the tidal response. So you can see that from these histograms that there are millions of models, millions of interior models involved in these histograms. And so they convolve all the uncertainties that we might have on the interior properties that determine the tidal lobe number K2. And one notable thing here is that there is a clear separation between models with an ocean, the blue histogram, and models without an ocean, the red histogram. So if we quantify the distance between the histograms, we can use these as a requirement for our measurements. So what I want to say now is that measuring the tidal response of these moons is going to be very challenging. These moons are small, and so the tidal response, the tidal lobe number K2 is small in magnitude. If you compare this requirement to Europa Clipper's requirement, that's going to be almost one order of magnitude larger for some of these moons. For Europa, it would be 0.06. Also, these moons are in nearly circular orbit, which decreases the amplitude of the tidal forcing and the force libration. And so that's going to make it even more challenging. But nevertheless, we investigated what kind of mission design, what kind of trajectory we would need to detect the tidal response and the force libration. And so I don't have any cool figures like Corey showed, but I have these figures. So we have three trajectories here. They represent three different classes of the trajectories that we are exploring at JPL. So the first one, T1, the one on the left, is a trajectory with a minimal number of flybys, as you can see for each dot with different colors for each moon. And so in that case, we only have 2 flybys for each moon. In the other 2 cases, T2 and T3, we have many more flybys, but with different characteristics, different flyby altitude and different geographic coverage. So we use these trajectories to simulate the gravity science investigation. We use JPL's navigation software, Monty, and we simulated the Doppler data that we can acquire with a Uranus orbiter and probe during the flybys of the moons. So there are several ways we can do Doppler tracking. The first one is highlighted in the corner in the right. We can use a single frequency, X-band, 8 gigahertz. And so we send a signal to the spacecraft, a radio frequency signal to the spacecraft. We get the signal back from the spacecraft and we compare the frequency that we receive with the frequency of the signal that we sent. That's going to be the Doppler shift, which contains information about the gravity acceleration that the spacecraft experienced during the flyby of the moon. So we extract from there the information on the gravity field. But we can do this also by using different frequencies simultaneously, X and Ka band, and that's going to improve our Doppler measurements, the Doppler noise by a factor 4 to 5. So that's going to be much more accurate. In addition to this, we also simulated the acquisition of optical data from a wide-angle camera to understand if this can help in measuring the libration of the moons. So here is a figure with the results for the tidal response. On the y-axis, you can see the projected precision for each case for the tidal lobe number K2. And on the x-axis, we have all the cases that we simulated. So T1, T2, and T3 for the different trajectories, X or Ka band for the different radio science system, and then opt for the inclusion of optical data for libration. So there are many dots here, but what I want you to focus on are the dashed line that represents the threshold for ocean detection that we identified from the histograms. And so that means that everything below represent cases where we can detect oceans with tidal response. So if we forget about everything that's above, there's not much left, but there is something left. And so even if it's very challenging to measure these parameters at the moon, we can still do it at Umbriel, provided that we have at least 4 or 5 flybys for this moon, and we're using an X and K band radio science system. And the difference between Umbriel and the other moons is that Umbriel has a much higher eccentricity by a factor of 5, and so the tidal forcing is larger at Umbriel, and so the tidal response is also more detectable. So we did the same for the libration measurements, and this figure has exactly the same structure with the projected precision on the y-axis for the librations. And there's a very nice paper out there by Doug Emunge and Francis Nemo, which shows how to use these libration measurements to detect the ocean and to characterize the ice shell thickness. But in this case, if we take a threshold of 100 meters from that paper, which is an arbitrary threshold above which, for the precision, above which we're not going to use that measurement is not going to be useful, and we remove all the cases, in this case, we get a much more positive picture. So all these cases up below the dashed line mean that in several different cases, we can use the libration measurement to characterize the hydrosphere of these moons and potentially to detect oceans. So the only case in which we cannot do that is Oberon, because it's farther away, it has a low eccentricity, and so the libration amplitude is very small. But for all of the other moons, we can potentially detect oceans by using the libration measurement. So to summarize this presentation, it's very difficult to detect oceans at this moon by using gravity and geodesy measurements. But I think that it's going to be important to take into account these measurements to complement magnetic induction, as shown by Corey. Magnetic induction could be challenged by potentially cold oceans, in which the electrical conductivity is suppressed, and so the magnetic induction response is suppressed. The detection of the tidal response at Umbriel could be a very powerful tool to detect an ocean there, because the tidal response is much less challenged by confounding parameters, and so the detection of a strong tidal response would be a clear indication that there's an ocean out there. But to do this, we would need to have at least 4 or 5 flybys for the moon, and for the librations, we have similar constraints. We need at least 4 or 5 flybys for each moon to potentially have an ocean detection with librations. So there's an associated paper to this work, that is coming out in a few days on JGR, but I'm happy to take any questions. Thank you.
Okay. Speakers, take your positions. And Robert, I hope you're still online to be able to answer questions.
Yes, I am.
Excellent. Alyssa was first.
Hi, Alyssa Roden, Southwest Research Institute. I have a question for Corey and Flavio about your models. So my understanding is that in a lot of the moon tours for something like Uranus Orbiter and Probe, you have targeted moon flybys where you're very specific about what you're trying to get and how close you are and all that. And then as you're moving from moon to moon, you also get a bunch of flybys for free. So I was wondering how many of your flybys for either magnetic induction or gravity and geodesy need to be targeted, potentially close flybys, or can you use a lot of those free flybys to get your data?
Yeah, I can kind of take that. So we actually have tens of thousands of models being run right now for the trajectories. So we're in the process of sorting through them, but you're exactly right. Some of the trajectories are targeted for just positioning. I think it's the ones that we do, we have at least 10 flybys for each of the moons, and they can be positioned anywhere we want, basically. And for magnetic induction and the gravity, we specifically try to, we're aligned in the requirements in terms of altitude and coverage and things like that. But I think it's, is it Oberon, the one that it's harder to get to more often, and we use that more as the gravity assist. Yep, exactly. And Miranda as well, I would say too. Yeah, those two bodies.
Okay.
Yeah, Miranda is complicated to get to because it has an orbital inclination that is higher than the other moon. So to target it, you need maneuvers. You need to maneuver to target Miranda. So that's not going to be easy. We're probably going to get flybys of Miranda in very specific occasion when it crosses the orbital plane. I want also to add that for gravity science, we might have an operational constraint on the fact that we need to track the spacecraft during the flyby. So we need the eigen antenna of the spacecraft pointed to Earth. So we're working on that in order not to overlap with other constraints.
Okay. And I'll just say Rosemary Balland and her group published a paper just last month with very detailed calculations of libration and obliquity measurement requirements for the worlds. I'm not involved with that paper, but I was very impressed by it. So I thought I'd mention it to you.
Yeah. Thank you.
Thank you.
Francis Nimmo, UC Santa Cruz. Actually, I wanted to make the same point as Alyssa just did. Have you looked at the obliquity? Because the obliquity is another way of probing the ocean interiors, and presumably you get that from the static gravity if you can do well enough. So have you thought about that yet?
Yes, I don't think we can get it from the static gravity. It's going to be hard to get it from C21 and S21. I'm not sure we will have measurements that are precise enough to do that. And probably if we do that from gravity, that's going to increase our uncertainty on all the other parameters. It might mess up with the other estimates of the other parameters.
I see. Thank you.
Okay, we're going to take a question online.
So for Robert Tyler, thank you so much for the fascinating talk. Would reanalyzing Voyager 2 data help test your predictions, or is a new mission required to get meaningful results? And the question is from Arwin Hubbard, LPSC ambassador.
I don't know enough about the Voyager data to determine that, but you would need to know about the tidal response pretty accurately in either case. So it looks like modern missions are probably the where you would have a chance at that.
Hi, Sierra Ferguson, Southwest Research Institute. My question's for Flavio. So in your talk, you mentioned simulating wide-angle cameras, and in the provisional UOP designed from the decadal, they don't baseline the wide-angle camera, only the narrow-angle. Were your results really strengthened by having those simulated wide-angle camera images for your libration study?
Yeah, that's the only camera that I simulated. I haven't simulated a narrow angle camera and try to get the libration from that. I'm not sure that's going to improve our estimate. How would that affect the estimate of the libration? But yeah, that's something that I should look into.
Cool, thanks.
Nick Wagner, Brown University, and this question's for Flavio. Would it be too hard to also constrain H2 to help, I guess, relax some of the requirements on K2?
It's going to be very hard. So we're going to have a few flyby for each moon. So we might have 4 or 5 flybys for each moon. And to get H2, you need overlaps between the ground tracks, right? You need crossovers, but you need a significant number of crossover to get H2. And I don't think we will have any crossover at all, potentially. So.
Cool, thanks.
Sean Brooks. Flavio, you seem to be the popular one because I have a question for you too. You mentioned your simulations being based upon tracks that were plus minus 4 hours. Can you get that duration of a track given the 3-hour one-way light time to and from Uranus? And if you can't, would you need more flybys?
So we simulated this, we looked into this. So that's the baseline scenario that we presented in the paper. But I think that we can get almost exactly the same results with plus or minus 2 hours from closest approach. So the influence of the gravity field exponentially falls off with distance. So when you're farther than 2 hours away from the closest approach, you don't get much more information. So that can be significantly relaxed. I think it's up down to plus or minus 1 or 2 hours.
That one-way light time is going to be a pain in the butt.
Yeah.
Thank you.
Noah Hammond, Providence College. Yeah, I had a question for the third speaker. I was trying to think about how to phrase it. It's a little bit tangential to the point of your talk, but I was just curious if you could quantify like the magnitude of the induced magnetic field in the Uranian system for Ariel compared to like the Jovian system. Is it like similar in strength overall?
Yeah, no. So it's the AC field that really drives things. So it's kind of similar for the inner moons. Miranda is more like 300 nanotesla. Europa 250 nanotesla. Callisto is more like 38. Ariel is 90 is the maximum you get. But if you look at the induction amplitudes, that's the driving field. The induction amplitudes are significantly scaled because the ice shells are expected to be so much thicker. So the source is much further away. So those signals I showed on the screen were only on the order of 15 nanotesla, and that's at Ariel. The further you go out, the smaller the driving field is. It's going to be really difficult to do ocean detection using magnetometry, specifically at Titania and Oberon. Still possible, I think, at Umbriel, but the other ones will be really difficult.
Yeah, I mean, I was just curious because I know, for the Galilean system, the heat dissipated by an induced electric current is like negligible for those moons, but I was wondering if it is at all significant for like Miranda and Ariel, where you have a shorter period and, pretty strong induce signals.
Yeah, Miranda's it's going to be difficult too. One, because it's a small body, and then also its orbital period is almost exactly lined up with its synodic. So disentangling that with such few flybys is really difficult to do. But it does have the strength of the driving field that we want for magnetic induction to work. So.
Cool.
Mm-hmm.
I'm going to take a prerogative and pitch a question to Scott King, because you don't want you to feel left out. So obviously for Ariel and for the other moons, they have probably migrated through various resonances. So there have been tidal heating episodes. Have you thought about incorporating that kind of bulk heating into the ice shell, into the enlarging the ever widening parameter space, if you like?
Yeah, I mean, that's certainly something we can do at the expense of creating significantly more models. I thought it's just interesting to kind of remind people and make the point that you don't actually need it to actually melt some of these things in the past.
Okay.
Amir Bagheri, Caltech. I also have a question to Scott. So I was just wondering, what is the specific advantage of using the neural network and machine learning approach compared to the typical MCMC that we used to be using, basically? You can just plot the corner plots, more or less the same stuff with the MCMC approaches too.
For certain things, that's true. For some of the other parameters that I didn't show here, it's going to be pretty tough to disentangle things because there's nonlinear interactions with some of these things. And I think that the chances of that popping out, it certainly did for Mars. And, that's the papers, the Aguilar et al. Papers that I cited in there, that where this originally came from was fitting, a somewhat larger planetary body.
Great, thanks.
Questions? Wait. Oh, good.
Make you all stay. Question for Rob Tyler. This is Carol Raymond from JPL. Sorry if I missed this in your talk or your abstract, but when you were calculating the radiogenic heating of the body, did you consider varying compositions, varying starting compositions, and also what was the assumption about the formation time?
So I used the model to simplify things. I used values taken from Hussman et al., an earlier paper. The values are so low that it doesn't really matter. In other words, to push the point, was just radiogenic was very small, and for the smaller moons, it clearly was a very small amount, and so I don't think that the value I used was critical, because it was just a curve, and then over most of the parameter space of the figures I was showing, the ocean tidal heat was orders of magnitude larger than radiogenic, and certainly enough to maintain an ocean. So radiogenic, the values I used were just quoted from previous work, and the only way I used them was just basically that they're very small.
Thank you.
Well, I also have a question for you, Robert. Even when the tidal heating in the ocean is high, unless you're in a resonance, you're still going to basically collapse the eccentricity, and the forcing will stop.
Yes, that's a really important point, because you need something. If you're going to maintain the oceans over a long period of time, the tides will efficiently pull down the eccentricity or obliquity, whatever perturbations. But once you've taken that energy out, the orbit shrinks a little bit. So basically, that energy compared to, but ultimately for these, the rotational energy of the primary is where all the energy is coming from, and that can be put temporarily into perturbed orbits. But basically, yes, that's a second question. So there's kind of two complementary elements. The one I was talking about, how you would be tuned into resonance, was self-tuned resonance, and that occurs on the time scale of freezing an ocean. The other one for like tidal locking and everything has to do with the feedback on the tidal forcing frequency in this case. And that would be, you would need to, to have something like that to be able to explain, the persistence of oceans over the time scales at which you would actually have regularized the orbits otherwise.
Hi, Anton Ermakov, Stanford. I also have a question for Robert Tyler. I'm curious, how does the geometry of the ocean, so things like, variations in the thickness of the ocean, variations in the thickness of the shell, which could be quite substantial. For example, for Enceladus, you could have, shell as thin as 5 kilometers and then as thick as 30 kilometers in different places. How does this complex geometry of the shell and the ocean affect the tidal resonances and the amount of dissipation in resonances?
Well, I can give you an example from Earth, where maybe 4 years ago, I calculated that.
I think you muted yourself.
Sorry. Yes, so the example of the Earth-Moon system is an example where I was able to get to the resonant response going back 4 billion years, and that was with parameterizing the ocean basins and continents. And so to answer your question, yes, it's important, but there's ways in which you can average out over long terms. So it depends on the types of questions you're asking. The resonances don't go away, they just become different. You'll still have maybe spherical modes. If there's bathymetry, then you would have the equivalents of trapped waves on that. So basically, in a short, if you start adding bathymetry of the ocean, you're adding more resonant modes, not less. So those just, every time you add a new type of wave that can propagate energy and momentum, that usually amounts to adding another resonant mode. And so a rotating fluid is already a complex fluid with lots of resonant modes that can be excited. And when you start adding the other elements like topography, that only increases. And so in short, the resonant modes don't go away. They should be maybe a little different, but that's all.
Thank you.
Okay, well, we only have a few minutes left in this Q&A session, unless the speakers on the podium have any last comments they wish to make. I think on the behalf of Carl, Mariana, and myself, I will declare this session closed, and I thank you all. Let's thank the speakers. Let's thank the techs. And let's thank Mimas. Okay. Oh, it was a good talk.
Thank you for dealing with the AV.